floor's pretty uneven right here. Damn it, let me fix this. It's a little lopsided. Chillster, what's up? Nasty Fripples, what's up? Imran, what's up? What's up? How's everybody doing? Alright, so I just finished setting this up.
Let me know, like, I don't know.
It's gonna be fine. Fuck it. Oh, let me fix the... So I'm gonna be asking a third question today. It's gonna be similar to the photograph or painting. You guys remember that question, the first trick question, right, that I used to ask? So I'm gonna be asking similar, but it's gonna be the third question. And where is it? And instead of photograph or painting, it's gonna be photograph or CGI. So that's gonna be the trick question. You know, I'm gonna have them pick the photograph from these two images, you know, and see if they can pick the photograph, right? But obviously it's a trick question because photographs of the Earth don't exist. So that's how I'm gonna introduce the subject today. So after the second question, the water level question, I'm gonna add this third question. And yeah, see if people can guess that they're both actually CGI. I guess, you know, it's gonna be a guess regardless, you know, unless you already know that, you know, photographs of the Earth from space don't exist. You know, that's the only way I could see people picking the correct answer, which will be they're both CGI, you know, but we'll see. And yeah, let's see. It's gonna be the third question today. Yep, and I see how that goes. It's going good, Imran. Thanks for asking. Alright, so let me make sure they're all in order, because when they're not in order, it just throws off the conversation. I gotta make sure they're in order. Yeah, it's already all set up. I'll show you guys the setup right now.
I learned my lesson in profit. I don't need to see the grades to know.
Let's see the stars. We got the perspective. Okay, I'm ready. Alright, so let me show you guys the setup. Let me see how this looks. I actually have a prop with me today. Here, I'll show you guys.
Good luck for you too.
Alright, so this is the setup. I have do you trust your common sense today? Alright, so yeah, I'm usually in that spot right there in the shade under the tree, but you know, today I wanted to get some sun. It's a little bit fresh, so the sun actually feels good. So I moved from there to there, but there you go. That's the table right there. And this is the prop that I added. I don't know if you guys ever seen this before, but it's called a tensegrity structure. As you guys can see, there it is. That's what's holding the level. You can see that. And it's basically being held, I mean, it's in the name. It's by tension of the strings. So the physics behind how this is being held up, I guess, is pretty cool, because the top piece is actually hanging. So the level is actually hanging, you know, from the bottom piece. And what makes it possible is that middle joint right there. The bottom piece is a higher elevation than the top piece, the stick going down that's holding up the top piece. So that string in the middle is what's holding up the whole structure, and the strings on the side are literally just keeping it stable, you know. So technically this top piece and the level are hanging even though they're on top, you know, so it gives this cool illusion, you know. I'm sure some of you already seen structure like this, but I think it's a good conversation starter. I think it's pretty cool, you know. It looks pretty, you know, looks gravity defying. So yeah, that's gonna be like a little prop I use right there. And yeah, I think it's pretty cool. Let me switch back. All right. Mr. Nick, 0 photos of the spinning space ball we live on, yet they live stream knocking it an asteroid off course millions of miles away. That's true. As long as they say it with a straight face, right? As long as they look serious and, you know, they're wearing a lab coat, you know, why would you doubt them, right? Why would they lie? It's not like they're getting millions of dollars, you know, for this stuff, for all these projects, right? It's not like they're getting a bunch of money. So why would they lie, right? So, I mean, all right, let me see. All right, so it's pretty dead than usual, and I'm assuming it's because of the Christmas break, or, you know, winter break, whatever people want to call it. DTC, hey brother, love your streams. Thanks. Thanks for stopping by and saying hi. Oh man, bear with me. I'm gonna take care of this. Okay, never mind. All right, so how does a globe rely on vision and basically imagination, right? Or people's ignorance, obviously, to sell their model? Well, it starts off with the claim that objects accelerate in free fall. So how do we debunk that claim that objects accelerate in free fall? Well, it's easy. Just like we could debunk the claim that water bends, you know, using water. Again, the physics of water debunks the claim that water bends. So in the same manner that people claim, you know, objects accelerate in free fall, we could also use water to debunk that claim. Why? Because we know water doesn't have a form, it doesn't have a shape, and it only reacts to a force. You know, water can only be displaced relative to motion. You know, we can recreate that experiment. You know, it's measurable, testable, repeatable. So here's an experiment I'm gonna be playing. It's only 2 minutes. It's the experiment I did with the buoyancy experiment, and then I'll just play it. It's 2 minutes, and then just to prove a point, anybody that's new here could see it. But so again, you could only recreate the effects of buoyancy, or what we call buoyancy, is by accelerating the container, because then the container is able to push against the medium, and then the medium can press on anything that's less dense and move it in the direction of acceleration. So here it is. So this is the setup for the first of 2 buoyancy experiments I'll be doing. A water bottle as the container, and the camera mounted onto the reference frames that I'll be accelerating, which is the dolly. The reason why we have to constantly accelerate to recreate buoyancy is because we're connected to the Earth, which is already in constant motion. And in order to overcome constant motion, you need constant acceleration. As you can see, the air bubble is centered, which means the bottle is level and at rest. The air bubble will always be displaced or pushed relative to the motion of the bottle. When I accelerate the bottle, the pressure of the bottle pressing on the water creates a pressure gradient. If you guys pay attention here, I don't even move not even a few inches, and the bubble reacts to that motion. And I'm probably not even moving more than like 5 miles an hour. Let's be real. You know, when I'm pushing this cart, it just comes to show that water and air, obviously, when contained, they're very sensitive to motion. They detect motion even at the slightest, you know, and it's instant. It's an instant motion transfer. So right here, I'm the one pushing the cart is pushing the L, basically the frame that I have the water mounted onto, and then that's pushing against the water bottle, and then the water bottle is pushing against the water, and then the water is pushing against the air. And that's how we get buoyancy. You need a cause, and buoyancy is an effect. You know what I'm saying? So again, you could see that even the slightest motion from me moving it, the bubble reacts to it, you know? So, you know, it's measurable, testable, and repeatable. You can't refute that air bubble displaces relative to the direction of the bottle, relative to the motion of the bottle, you know? Water is then able to push anything that's less dense, like the air bubble, in the direction of acceleration, which is what we will call buoyancy. You can't have buoyancy without a pressure gradient, and you can't have a pressure gradient without a contained system that's in motion. For the second buoyancy experiment, I have a cargo van as the container, a helium balloon, and an apple. I also have the camera mounted onto the reference frame that I'll be accelerating. As soon as I accelerate, the pressure of the van pressing on the air creates a pressure gradient, with the most dense air towards the back of accelerator. Again, different setup with different substances, helium and air now. Again, we accelerate the van is then able to press on the air, and then the air then is able to press on the helium. Again, it's a chain reaction, you could say, motion transfer. You know, there needs to be something pressing on the air so that the air can press on the helium. The air can't just press on the helium for no reason, like with no cause. There needs to be a cause, and buoyancy, again, is the effect. You know what I'm saying? And the less dense air towards the front. The air is then able to push the helium in the direction of acceleration because it's less dense. But the air cannot push the apple because it's more dense. Therefore, the apple remains at rest. The apple only appears to move in the opposite direction of acceleration because the camera is also moving with the reference frame. The helium balloon has true motion, and the apple has apparent motion. In order for the Earth to be motionless, you need a force moving in opposite directions at the same time to be able to accelerate the apple in one direction and push the air and helium in the opposite direction with... Imran, I know it will be cool to go to like the gym, or, you know, the thing is, I wouldn't know if they have the right to like kick people out from like they're in front of the door, right? Maybe if I'm in the sidewalk, obviously they can't, but if I'm in their property, I mean, technically it's open to the, well, again, you have to be a member, so yeah, I don't know. I will have to just stay close to the sidewalk, or on the sidewalk if I do decide to go to a gym or something like that, but without any motion of the container. You would also need this same force to accelerate a container without any displacement or buoyancy. In other words, you have to believe in a magical force that can accelerate a container without any pressure or buoyancy, and also be able to create pressure and buoyancy in a motionless container, which is the literal opposite of what physics shows. Physics proves that you can't have pressure and buoyancy without motion of a container, and you can't have motion of a container without pressure and buoyancy, proving that the Earth cannot be a motionless plane. Again, and this also debunks the globe, because if it's the Earth that's pressing up against the air, which gives us our pressure gradient, which gives us our buoyant effect, then that wouldn't work in a globe perspective, because on a globe, it would have to be moving up in every direction, 360 degrees. That would mean the Earth is expanding. It would have to be expanding, or just be torn apart. Not only that, because gravity is not a pulling force anymore, water and people and everything wouldn't be able to stick to it. You know what I'm saying? I guess the pressing out of the Earth, that will be the explanation why, but again, it just doesn't make any sense. The Earth, you know, and again, water, the physics of water debunks that claim. So they want to make you believe that buoyancy, that air and water do the opposite effects. In other words, they don't have any effect when they're being accelerated in free fall. So let me see, this is the free fall one. Okay, this is the free fall one. So they want you to believe that when the air bubble is rising up, the bottle's actually motionless, and when it's being released, it's actually accelerating. But the air bubble shows the opposite. It shows that it moves when the bottle's moving, and it shows that it shows no motion when the bottle's at rest or not moving. So they want you to believe that basically your reality is lying to you now. Like apparently there's a glitch in free fall because the bubble doesn't get pushed down in the direction of acceleration, which should happen if there's something acting on this bottle. Again, there has to be a cause to why this is apparently moving down, right? And I say apparent because obviously we know that it's not accelerating down, and it's the Earth's motion giving us this effect of apparent falling, right? Or apparent motion. You know, the true motion is when you release a helium. That's a force that's being pushed, you know. So again, it goes back to the physics of water. Why? Because just like the air bubble is not lying to you when it's level, right here. Oh shoot, let me show it right here. Right here. Just like the air bubble doesn't lie to you when it's level, the air bubble doesn't lie when it's being accelerated either. So you would have to accept that, yeah, the physics of air and water shows us that the Earth is level, right? But the physics of air and water, you know, it doesn't prove that, you know, that objects don't accelerate down, basically. But you have to basically deny the physics of water when it's under conditions of acceleration. You have to deny that part, you know, as a stationary flat earther and obviously as a global earther, you know. You have to deny the fact that water is literally showing you, the physics of water is showing you what's happening. You know, again, if you're going to trust water level, water showing you that it's level, then you must also trust it when it's showing you that it's accelerating. You know, when it's being accelerated and when it's not being accelerated. You know what I'm saying? So, and if people want to claim that, oh, you could have an acceleration of a container without displacing the air bubble, right? Well, then you're going to need an experiment, you know, to prove that. You know, you can't just say, oh, well, here, I dropped something. No, that's no different than a globe earther proving gravity just by dropping something, like Neil deGrasse Tyson. You know what I'm saying? You need an experiment to recreate, you know, what we observe. You can't just take the phenomenon and claim that, and then just claim anything and expect people to accept your explanation based because you dropped something. That's stupid. You know, you're gonna need an experiment to recreate your claims, to recreate the effects that we see. So you're gonna need a cause, and then you're gonna need the effects to show, you know, that what we experience, basically. Just like I did. You know, I did 2 different experiments utilizing motion of the container to recreate all the effects that we observed, from weight, orientation, you know, pressure gradient, buoyancy, the apparent motion of the less dense object, you know, everything with one motion could be recreated. Now, if you claim that it's a different cause and it's not a container that's in motion that creates all of these effects and also freezes all of these effects when it's being accelerated in free fall, which are 2 extraordinary claims that basically defy physics, you're gonna need an experiment to back up your claims, basically. So you can't just be giving word salad explanations and then just dropping something. You know, that's literally globe earth logic. Literally globe earth logic. So, I mean, that's just the way it is, whether you like it or not. If you're gonna claim the Earth is stationary, you're gonna need to demonstrate a force that can accelerate a container without any displacement. So I don't give a fuck what word salads you use, what explanations you give, and all this bullshit, because I do get a lot of fucking messages from a bunch of trolls, you know, just stuck, you know what I'm saying? Literally stuck, you know, whether it's, you know, willful ignorance or just ignorance, that's irrelevant, but that's what you're gonna require. A force that can accelerate a water bottle without any displacements of the liquids within it, in the gas. So once they bamboozle people with accepting that objects accelerate down, which again, it's already a false premise, but again, that's how the whole globe Earth is built off of, a false premise. So once they get you to believe in the globe and the objects accelerate down, now people have this idea that there's a force, magical force accelerating and leading towards the center mass, right? And in people's mind, that's the explanation to water bending, right? Because gravity, right? Objects accelerate down, therefore water goes down towards the center. And if you contain water on a large scale and everything's going down to a center, then that's the explanation to why water bends. We don't even need to go to physics. It's just, you know, it's just based on an assumption, basically, that objects accelerate. Again, people are creating ideas or theorizing about things based on another theory. You know, so they're building off a false premise, literally, that objects accelerate down. And that's where the whole globe model comes to be. And again, once they get you to accept that objects accelerate down when they actually don't, they still play on vision, you know. to explain away what we see. So this is I was gonna play this like a month ago or two, but I didn't get to play it all the way through, so I'm gonna just go over it again. And I think it's very important to understand how where the globe Earth models come from, and basically understanding perspective. That's what it comes down to. So I'm gonna go ahead and play this, and then we'll just summarize it after. It's in two parts. We'll let it play half through, we'll summarize the first part, and then we'll let the second part go.
Here's a definition of a nautical mile from a mathematical textbook, yeah? And a nautical mile is defined as the length of the arc of a great circle which subtends an angle of 1 minute at the center of the Earth. So you're supposed to believe that the Earth is a big solid ball, yeah? And it has a center. And a nautical mile, as seen here on the right-hand side in an orthographic view, is then the angle, the length.
So right off the back, the globe has to assume that it's a ball. You know, they have to assume the Earth is a ball, and then they take these visual observations to fit their model. So again, it's all starting on the assumption that it's a ball already, you know, their measurements, which is obviously a false premise.
Of this arc here, so this very small arc, it's the length of that when the angle at the center is exactly 1 minute. And it's seen here, 1 minute, there's 60 minutes in 1 degree. We usually know that a circle has 360 degrees, and each degree has 60 minutes, which basically makes 21,600 minutes in a circle, yeah? And one of these minutes is then the arc length from the center of the Earth is what they define to be a nautical mile. So that's one definition of a nautical mile. I'm going to produce another one here, which is different. This is a practical definition of a nautical mile, and also the way people navigate on water. So the way it's defined is that a nautical mile is the length or the distance that you need to travel to see a change in altitude of 1 minute of something. So altitude is basically the visible position of, let's say, a lighthouse. So here's a lighthouse on the left-hand side. There's me at this position, and you, Dale, slightly closer to the lighthouse. Now we are going to see that light in a different visible position from each other. And if we wanted to calculate the distance between us, if you see that light 1 minute dropped in your visible vision than me, then we know that we're 1 nautical mile apart. Yeah. And that's the way people navigate. You know, normally they don't use lighthouses, they'll use the sun or the moon. They'll take a sighting, and that way they can, to travel. So that's the whole concept of the celestial sphere, which I'm not going to get into in too much detail. But the important thing is here, if you distance yourself from an object, in this case a light tower, and the thing drops 1 minute in your visible place, or its visible position in your field of view, then you know you've traveled 1 nautical mile. And that's the way people navigate all around the world, Bill. Yeah. Today. Yeah. And you'll see that these two different definitions are completely different, right? So this one is relying on a mathematical model telling us that we're on a ball and defining what a nautical mile is based on the idea that, the Earth is a radius and there's a ball. In fact, they say that a nautical mile, the radius of the Earth is 3,438 nautical miles. So that's a mathematical concept. And this one is a practical concept. You're on water, we know water's level, and if you move backwards from a luminary or from a light in 1 nautical mile, then it will change its visible position. It will basically drop in your visual field 1 minute, 1 arc minute. So, given those two different definitions, the question that really comes up is, which one's real? This is the one they all want us to believe, right? And this is the reality of the situation. And here's a little bit of text, just for people who want to follow along. And A nautical mile is the length of the arc of a great circle, which subtends an angle of 1 minute. And it also introduces the concept of a radian, which I think I'd like to leave to another day. So I'm just going to use this concept of a radian without completely defining it, and we'll come back to that.
Sure.
But what happens here is that the number of minutes in a radian is equal to the number of nautical miles in the radius of the Earth. Now what pops out basically is this number 3438.
Yeah.
So that's what they actually tell us the radius of our space ball is in nautical miles. You'll hear different, numbers depending on whether they use statute miles or kilometers or whatever. But as far as nautical miles are going, that is apparently the radius of the Earth, 3438.
So real quick, a summary of that. So basically the globe Earth assumes that the Earth is a globe already when you're making these observations at sea, for example. So when you travel, we'll say a mile, right? You see 1 minute difference in height and altitude. But let's say you travel 60 miles, that would be 1 degree, of change. 1 degree in 60 miles, again, due to perspective. But the globe Earth obviously assumes that the Earth is a ball. So basically what they do is in those 60 miles and there's 1 degree of change, all they have to do is it's basically multiply 60 times 360 degrees because that completes a circle of 360 degrees. And if 1 degree is 60, then to complete the circle, all you have to do is multiply 60 times 360, which gives you the circumference of the Earth in nautical miles, which is around 2,100 miles or so. I forgot the exact number. Point being is that that's where the radius of the Earth comes in from nautical miles. It's basically just the limit of perspective, and how far we could see. Again, it's derived from vision and perspective. The whole geometry or dimensions of the Earth. The circumference, the radius, the diameter. It's all congruent. But yeah, it all comes from the assumption that the Earth is a ball, and again, seeing these visual observations and making them fit your model, basically. So that's pretty much it. And then the second part is the main part that I kind of want to focus on, because the next video that I'm gonna go over, they basically don't take account of any of this perspective when they're doing visual observations, and I'm gonna highlight that. But this next part is actually the main part I wanted to highlight.
And as I say, there's two different, if you like, definitions. There's the mathematical model, and then there's the practical model. So bearing that in mind, and this number 3438, I'm going to jump differently to a different subject, and then we'll come back to it. The different subject I'm going to talk about is visual acuity and the visual angle. So this diagram is taken from a book about 20/20 vision. In fact, it's a book, Dale, that in fact, I think I've got it here. Just let me bring it up. Yeah, I have.
No, that's true, Squirrel Sniper. Since we don't know the true dimensions of the Earth, all these numbers of distances from the center to the south, all of that, you could just say, they're assumptions, Again, nobody knows the full dimensions of the Earth, the true layout. So again, all of these measurements on Earth that people used to, try to use to debunk flat Earth or you prove the globe or stuff like that or whatever, the fact is nobody knows the dimensions of the Earth, so that becomes irrelevant, So yeah, that's true.
This is a book written by an American physics department, and it's to do with what size of letters do you need on an eye chart, right?
Yeah.
So that they are visible. So when you're doing, your eye test, you usually got one of these eye charts with numbers on it, and you stand 15 feet away from it, and you're supposed to, see if you can read all the letters, and they'll tell you how good or how bad your vision is, right? And this document is talking about the size of the letters that you need to draw and the gaps in between them, so that, you can draw signs that are clearly visible. And it depends on the distance and the observer's visual acuity. So it's trying to basically measure visual acuity, yeah? And if I go back to the PowerPoint, then one of the important topics in here is the fact that your retina is a curved surface, yeah? And if I'm an eye looking at a chart on the wall, then the question that is asked is, or the definition of a visual angle is this angle here that basically encompasses the whole object. So the object starts at A, it finishes at B. You can think of it as one of these eye charts hanging on the wall. You're at a distance D from it, which, you know, might be 15 feet, let's just say, to take an example. And then the question is, what is the angle subtended at the eye from that object, AB? Yeah? And you can work out that angle. On the next slide, I'll just show how it's done. The visual angle is basically the height of the object, or the width of the object if you were looking at something horizontally, but let's assume it's still an eye chart. It's the height of the object divided by the distance from it, gives you the visual angle in radians. Yeah? And again, I'm using this concept of radians without specifically defining it, but the radians is a way of intrinsically measuring based on the radius of a circle. So instead of using degrees and minutes, you basically use the radius of the circle to measure how far you are around it. So if you like, it's something different to degrees and minutes, and it's called radians. Yeah. So this is clear. The visual angle subtended at your eye depends on the size of the object and the distance you are from it. Yeah. And if you want to convert from radians to degrees, there's a way to do that, which I'll just follow the bouncing ball for those who want to follow along. It basically turns out to be the visual angle in minutes is 3438 times the size of the object divided by the viewing distance. Yeah? So this magic number 3438 pops up again in visual acuity. Visual acuity being how far can I actually see before things are no longer discernible to me? So what's the limits of my vision, basically? And this formula, just to give everybody an example, would mean that if you had a coin of 1 inch of diameter and you put it at 3,438 inches from you, which is 286 feet or 95 yards or 87 meters, right? Then the visual angle of that coin will be 1 minute. And basically at 1 minute, Dale, that's where your visual discernment stops. So some people can go a bit lower, right? Depends on age and lighting and, you know, various conditions. So this isn't exact, but basically if something is less than 1 arc minute, then you can't see it anymore. And anybody can try this, you know. Take a coin, put it at 87 meters and see if you can see it still. Or take a dartboard, you know, it could be 1 meter. You would then have to go back 3,438 meters and you wouldn't see it. So it doesn't really, it doesn't depend on the size of the object. The formula is there all the time. And this magic number 3438 is there in the whole topic around visual acuity. And it just happens to be the number of nautical miles in the so-called radius of the space ball. So people could think this could be a coincidence. I don't think so, right? That basically this ratio of 3438 is where, if you like, the imaginary curve is supposed to happen. Do you know what I mean? Just beyond our limit of vision, is where the curve starts.
All right, so very easy. Visual acuity, obviously, meaning perspective or the limits of perspective. And the magic number, the 3438, is basically the radians of our limits of sight, basically, or of the angle acuity, basically, you could say. So, in other words, the horizon, the limit of perspective, is basically the radians times the height of the observer over the distance. So if you had an observer or a camera at 6 feet above sea level, right, and you're looking out at the ocean, you know, at the horizon, right, at 6 feet, you would then have to multiply 6 feet times 3438, which will give you a distance in miles about 3.9 miles. So your horizon at 6 feet elevation, based on that formula, should be 3.9 miles in the distance. So that'll be the limit of perspective of the horizon. So anything that goes beyond that will start to get obstructed by that, by the ocean, you could say, by again, it's all relative to the height and the distance times the radiance, again, that magic number 3438. So again, you guys could look this up. The height, you know, the horizon distance for a 6-foot observer would be above 3 miles. That's the Google answer. Again, they, you know, again, if you double the height to 12 feet, then your horizon is twice the distance, you know. Well, again, you guys could do the math. But basically, if you're making an observation over a body of water and you're only about 6 feet above sea level and your horizon's only it's under 4 miles away from you, right? If you're observing an object that's taller than 10 feet, in other words, an object that's going to require more than 4 miles to basically vanish. If an object is taller than, again, than the distance needed to vanish due to perspective, what's going to happen is, if the object again is taller, then the ocean's gonna start to obstruct that object from the bottom up, because again, your horizon is only at 3.9 miles based on your height. So again, anything that's taller than 10 feet, 15 feet, anything that requires, again, a longer distance than 4 miles to vanish, it's gonna get obstructed by the horizon, or again, your limits of perspective, which is the horizon. And you're gonna get that apparent effect of objects appearing to go down a curve. But again, they're just going out of perspective, out of your limits of perspective, basically. And again, this will happen with any object, you know, at 6 feet elevation, any object that's 10 feet or higher, you know, you're gonna get that effect, you know. An object that's smaller than 6 feet, you know, it's obviously gonna disappear due to perspective before it goes over the curve, right, or beyond the horizon. But again, that's only if you're observing an object that's shorter than 6 feet, you know. But if you're observing an object that's taller than 6 feet, then again, you're gonna need a longer distance for it to disappear to a point. And if you don't have that distance, obviously, if you're at 6 feet, then again, the horizon is gonna start to obscure the bottom of the object you're observing, whether it's a boat, whatever it is at a distance. The bottom's gonna start to get basically blocked by your limits of perspective again. And the only reason why you're able to see the top is because it's at a higher elevation than the observer, you know. That's why. And obviously the bottom part of the boat, when it's at a distance, it's at a lower elevation than the observer, so that's why it gets obstructed first by the water, right? So I just wanted to prove that point about perspective and how, you know, your height is relative, obviously the distance you're observing, you know, all of that. Because again, they try to take that and say that it's the curve of the earth, but in reality it's the curve of your eye. It's just the limit, again, of your eyesight. I know I kind of repeated myself there, you know, but yeah. Now let me play this next video, which these are the top 3 proofs of the globe, by the way. So let's go over it and see what proofs they have. These are the top 3 proofs of the globe. And again, nothing to do with physics, is all just visual phenomenon to interpret or to fit your presupposed model, basically. So here it is, the top 3 proofs that debunk flat earth, right? But again, the earth's not flat anyway, but level, right?
Oscar, you asked the question, what are some of the easiest ways that you can prove that the Earth is round? Because apparently this is something that we're debating. I have no idea why. That's a hard thing for me to even start talking about, because there are so many proofs that the Earth is round, it's difficult to know where to start. And it's not okay to think that the Earth is flat. This is not a viable...
Again, this is how they misrepresent. Again, oh, it's not okay to say that the Earth is flat. Yeah, I agree. It's not okay to say that the Earth is flat, because it's not an accurate description. Flat has nothing to do with orientation. The Earth has orientation, so the Earth is a level plane. So I agree, you know, it's not okay to say that the Earth is flat, but again, it's just a term, nothing too serious. But, you know, this is how the propaganda works, you know. They misrepresent, and yeah. Let's see if they have any physics, you know, or is it just visual proofsies?
Argument. I have friends who have been on the International Space Station. They have orbited the Earth once every 90 minutes. You know, I have had personal experience with people that have been up in space and can see with their own eyes that the Earth is round. And of course, we've taken all of these amazing pictures from space. They're so...
Again, so you have friends that work at NASA that proves that the Earth is a globe. Like, You know what I'm saying? What kind of logic is that? Now, pictures, again, they're images, but again, you can call them photographs if you want, but that still doesn't change the fact that they defy physics, you know, proving they're not photographs.
Beautiful, all those pictures of the Earth. So I don't really know what's going on right now with this Earth is flat thing, but I will tell you that this is one of the things I really enjoyed teaching my own astronomy class about, because there are proofs all around you. It is not difficult to know that the Earth is round. In fact, people have known this for way more than 2,000 years. The ancient Greeks actually had a number of really elegant, wonderful proofs that the Earth was a sphere. So let's start from the simple to the slightly more complicated. One of the things you can see yourself with a pair of binoculars is if you actually go out to a lake and there are boats on that lake, the farther away a boat is, the more the bottom of the boat will disappear, and you'll basically just see the mast of the boat. And as a boat goes farther and farther away, the last thing you will see is the very top of the mast of that boat. And that's because the boat is actually going over the horizon that's curved. And that means that as it goes...
Again, they completely obfuscate perspective, you know, and visual acuity, you know, because that's obviously the real reason why things appear to go beyond the horizon. But again, they interpret that and say that it's the curve of the Earth. Again, it's no different than claiming that apparent luminaries drop in your field of view because you're going over a curve. It's basically the same logic, you know. But again, they don't take account to perspective. They don't take account any of that. You know, apparently we have infinite vision, apparently, in their mind. So again, starting from a false premise, we have infinite vision. So if things get obscured at the horizon, it's because there's a physical curve. Like, that's the most retarded shit I've ever fucking heard. But yeah, that's the #1 proof so far, or one of the proofs. I wouldn't say the #1, but
goes farther and farther away, you see less and less of the bottom of it and more of the top of that. You can see that with binoculars, by an ocean, by a lake. It's really easy. That wouldn't happen if the Earth were flat.
Yes, it does. You could downscale this experiment to a smaller scale. Again, not saying that the Earth is flat, but it's level. But point being is that you could recreate this effect of an object appearing to disappear due to perspective on a level surface. For example, like a soccer field or a basketball court. Again, do a smaller scale observation of what you're observing, and you're gonna get that same effect. Again, misrepresenting, you know, and literally just flat out lying, right?
You would simply see the boat getting smaller and smaller and smaller as it went farther away, but you'd be able to see the whole thing with the same proportions. Now, another way...
And not if the horizon, the limit of your horizon is before, you know, the distance needed for that boat to disappear, you know, as, you know, due to perspective, you know.
That you can tell that we're on a sphere is to think about how there's something called the tropics on the Earth. And the tropics are places near the equator of the Earth where sometimes the sun is overhead in the sky. And this was actually something that the Greeks used not only to prove that the Earth was round about 2,000 years ago, but they actually measured the circumference of the Earth accurate to within just a couple percent 2,000 years ago.
By the way, this experiment, the Aristophanes experiment, takes two big assumptions to do this measurement. The first assumption, again, is that the Earth is a ball. Again, taking visual observations like the sun, you know, the length of the shadows, for example, and stuff like that, and making them fit your presupposed model. Again, they're assuming that the Earth is a globe already. That's the first assumption. And the second assumption is that the sun is 93 million miles away. So in other words, it's so far away, and it's much bigger than the Earth, that by the time the light rays, you know, touch the Earth or hit the Earth, they're coming in parallel. So again, two assumptions there, that the light from the sun is coming in parallel and that the Earth is a globe. Those are two big assumptions that they're making for this experiment, which can be recreated on a level plane, by the way, with a local light source, you know. But
we've known that the Earth was round. There was a really brilliant Greek scientist called Eratosthenes, and Eratosthenes noticed that there was a town called Syene, and on a certain date, the sun would actually shine straight down to the bottom of a well. That meant the sun was directly overhead. You could look down a well and see the sun shining back at you. And on the very same date, farther away in the city of Alexandria, that didn't happen. The sun was not directly overhead. It was a slight angle. And all that Eratosthenes did was he measured the difference in the angle of the sun. It was straight overhead in Syene. In Alexandria, it was a little bit less than overhead. And he rationed that that change in angle from one city to another was probably indicative of us being on a curved surface. And you could make all kinds of measurements even between those two cities and see that the angles were different. The sun was at a different place in the sky.
That's because if you have a small local sun that's moving above, the Earth instead, then you're gonna get, different angles of the sun in the sky. Like, what the hell? This is pathetic. Yeah.
He actually measured the circumference of the Earth, and he got it right 2,000 years ago. So another really simple proof is that on any given date, at different cities and different places around the world, the sun is at different angles in the sky. That wouldn't happen if the Earth wasn't round.
Yes, it would. Again, take a local light source, put it above an object. It's going to cast no shadow if it's right above the object. Then move the object away, 5 feet to the left or 5 feet to the right, and you're going to start to see a shadow. Like, wow.
Then there are some other proofs that are a little more obscure, but they're actually really lovely. And one is to observe what happens during a lunar eclipse. Now, a lunar eclipse happens when the Earth casts a shadow on...
Okay, before, again, when it comes to the luminaries in the sky, the motion of them, what are they, what's really happening with the luminaries, the sun, the moon, and the stars, nobody actually knows. That's a fact. Nobody knows what they are, the true, the cause, I guess you could even say, of the motion, all of that, all of that is up for speculation, right? But they're gonna take that, and again, take that visual phenomenon again, and make it fit their presupposed model again. Again, just using vision. Oh, look at this. And look at, like, you're just looking at stuff that's retarded.
Moon. The moon actually goes dark. In fact, if you've seen one, you can actually see the Earth's shadow go across the moon. And when the moon is entirely in the Earth's shadow, the moon looks kind of dark and even kind of red colored. It's really, really beautiful. What's happening in that case is that the sun is on one side of the Earth. The Earth is in the middle, and it's casting a shadow. The Earth is casting a shadow on the moon. And as the shadow moves across the moon, you'll notice that the shadow is curved, it's round. So something like the sun that's bigger than the Earth and is able to cast a shadow of the Earth on the moon can actually show you the shape of the Earth. Aha, you might say, but could the Earth be a disk? Could it be flat, but it's actually still shaped like a disk, not like a sphere? There was a Greek scientist called Aristarchus, and what he noticed was that you can get a lunar eclipse at many different angles where the sun is. Sometimes the shadow goes straight across the moon. Sometimes it just kind of glances the moon. Just a little bit is in shadow, just on the top or on the bottom. From every different vantage point, every different angle that the sun is casting a shadow, you always get a perfectly curved shadow. The only shape that can cast a shadow that's curved from any direction you put the light is a sphere. So people have known that the Earth is spherical for thousands of years.
Wow, how? Just by looking at stuff, apparently. Just by looking at the sky and looking at objects appear to disappear, right? That apparently proves the globe. Wow, just by looking at stuff, you could prove the globe. That's pretty crazy. Pretty crazy. All right, that's enough of that. So again, they're literally just playing on people's vision and completely ignoring how substance behaves, aka water, air, and yeah, they're literally just making up stories and just taking visual phenomenon and making them fit their model. It's pretty pathetic. It's pretty lame. And I hate to say it, but even motionless flat earthers now are doing the same. They take the phenomenon of objects appearing to go down or accelerate down, even though the physics shows that that's not what's happening, water in specific, water and air. But now they're taking that phenomenon and now coming up with a bunch of different theories about what's the cause, of this phenomenon we observe. That being the acceleration with no displacement, now they're coming up with a bunch of different stories of what the cause is, And then you ask them, okay, demonstrate a force that can accelerate, solids, liquids, and gas without any displacement, like what happens in free fall, right? And you would expect, an experiment that recreate that, but no. What do? They just, here it is. They just drop something, or here, the water bottle, right? You ask, let me see an experiment that can accelerate, gas, water, and solids at the same rate, right, without any displacement. And then they go and do this. Who else does that when you ask for proof of their imaginary force? Who else does that? Globe earthers. You ask, okay, show me proof of gravity pulling objects towards the ground. And what do? Whoop. Pathetic. And now you have stationary flat earthers doing the same. Why? Because a force that can accelerate this bottle without displacement doesn't exist. You see the water swishing? The water is always going to swish relative to the motion of the bottle, no matter in any direction. You know, and I'm not even pushing it that hard. But yet you want me to believe that this is accelerating in free fall 9.8 meters per second square, which is over 88 miles an hour in 2 seconds? Come on. And with no displacement of, come on. Retarded, you know. But again, people could believe whatever the hell they want. At the end of the day, I don't have beliefs. I don't believe that the earth is in motion. That's what physics shows me, you know. Again, if you could physically show me that it's a different cause that's recreating all the effects we witness and experience, you know, then I'm open for that. I would love to see your experiment, you know, using this, you know, whatever cause you claim it is, and then putting it, you know, in an experiment to show that, look, this can accelerate the water bottle without any displacement, and boom, show it, you know. But you would literally need a force not only to create pressure and buoyancy in the bottle without moving the bottle. So in other words, you got to be able to move the bubble around without motion of the bottle, which you know, you got to be a water bender for that, if you ask me. You know, you got to be able to move the water like this without moving the bottle. And you also got to be able to accelerate the solid, the liquid, and the gas without any displacement as well. So you have to accelerate this without the water swishing around. So it's like, so in other words, like if it froze like this, imagine the water just froze like this, but without freezing, and then accelerating it without it moving around, right? Without it displacing, you know what I'm saying? That's what displacement is. It's a reaction to motion. You know, for those of you that might be confused with that word, but I'm actually at UCR today. Yeah, this is the school that I normally come to because it's the closest one to my house. And yeah, I mean, it's a good size. It's probably the biggest university here in Riverside, or close to where I live. So yeah, there's definitely a winter break. It's pretty slow. I'll be lucky if I get one conversation, to be honest, but we'll see. We'll see how it goes. Hopefully I could get one. I do have I'm bringing back the trick question, so it's gonna be the 2 globe images. So I do want to try it out, so hopefully. Winter break, yep. Yeah, I think this is gonna be my last live stream the rest of this month, at least here at the university, for sure, at least, because I'm gonna wait till January to come back, because it's gonna be dead like this, I'm pretty sure, you know, and the rest of the year at least, because of the holidays and stuff like that. But yeah, no, yeah, it's pretty calm. Oh yeah. Compared to like the other days where I come, where there's music and other tents and all that, like it's night and day, literally. Nah, it's impossible with 2 kids. We couldn't do live streams like that right now. especially with a 5-month-old baby that wakes up, randomly every hour, every 2 hours, So, and especially, and plus we have a 3-year-old, so, requires a lot of attention. So yeah, it'll be impossible for both of us to do this right now. So, believe it or not, Nat is helping out a lot by, being there for, for our kids and, enabling me to come out and do this. If it wasn't for her, I wouldn't be able to do this. I wouldn't have the time, so yeah. Oh yeah, I have kids. I have a job, I have kids, and I'm still able to do this. It just comes to show that if I can do this, anybody can, You don't need a big following, you don't need money, you don't need donations from people, if there's a will, if you have the will, then there's gonna be a way, You could always make time for something like this, Believe it or not, I mean, if I'm doing it with kids and a job and, then anybody could, I know, not a lot of people are self-employed, I'm luckily self-employed, so I'm able to kind of like, work on my schedule, in other words. And I know, working a 9 to 5, could be very tiring, and stressful, and I get it. You might not even have the energy to do activism maybe on the weekends because, you work, 8 to 10 hours a day, and I get it, but not everybody's in that position, And again, if you really are passionate about spreading truth, and then you'll make time, you know what I'm saying? There's no excuses in my opinion, but I get it. They got us basically in a position where we're comfortable, They want people to be comfortable because once you're comfortable, laziness follows, And once you become lazy, then, you're going to become intellectually lazy. And then once you become intellectually lazy, then at that point, you don't give a fuck what happens, how your life is being dictated, And you're just going to go along to get along, So if you want to see change in the world, right, you got to be the change first. Have you made any changes in your daily routine? Any changes, anything to, that, to help spread this word, like, because anything is better than nothing, at the end of the day. So, and trust me, man, I get fucking lazy too sometimes, it's just part of being human, I guess, right? We get lazy sometimes, but again, we can't get comfortable in that, and again, I'm subject to that too, I'm not perfect. Again, I'm lazy too, and it's not easy, not that easy, but eventually, once you do it, it does get easier, It's like with anything that you do in life, eventually it gets easier the more you do it. It's like tying your shoe. In the beginning you struggle, you can't really do it, and then, you get better, your motor skills get better, and basically become second nature. Boom, like nothing, right? Let me see. Homeschooling 100%, yep. I never really know what people want to hear, if you know what I mean. No, I know. I can talk forever about nothing. True. I mean, it just comes to show people don't really listen. Like, it looks like they're listening because they're there, apparently listening to you, right? But they're not truly listening. Like, they're not actually thinking about what you're saying, you know what I'm saying? So that's why they basically kind of on autopilot. And not everybody, but a lot of people, they have very short attention spans. Have you watched Leave the World Behind yet? No, I don't know what that is. Is that a channel? Or a documentary? Or yeah, right. I know, yeah, we and I have a lot of conversations, like, and yeah, it would be cool if we could record some of those, because there's a lot of things that come to mind in the moment, and pretty relevant things, that, you wish you could remember, because it makes a good point, stuff like that, but I guess that's why podcasts, are a thing, get to share your thoughts and record it just in case, You know, again, brainstorming. That's another thing, you know. It's a good thing. Ooh. Interesting. Let me see. 43 minutes. Oh, interesting. Oh, it's a Netflix fear-mongering film helped out by Obama, contributing scripts, notes, and financing. True. The news, you know, it's mostly just fear-mongering. Almost anything in the mainstream, you know, it's literally just lies and fear-mongering, you know. The big stories, usually, you know. Obviously they throw in some small stories, local stories there, you know, just to give the impression that they do cover, you know, real stories and stuff like that. But again, that's just them mixing truth with lies. That's another thing people need to realize. The way that this whole, you know, thing is playing out is that the people that are lying about the globe, or lying about the nature of the earth. Oh damn, it's noon? Oh yeah, it is noon. I could hear the bell. Nice. Wait for that to finish. Yeah, I kind of lost my train of thought. Nah, it's not an old bell tower. It's just, I mean, it's just a tower. I'm pretty sure. Yeah, I don't know how it works. I mean, is somebody in there like swinging it, right? Or is it like a speaker there? Like, I don't know. I'm assuming it is a bell, like a real bell, but I wonder if it's programmed like electronically, right? Because I didn't see anybody go in there. Like in the old days, right? Or they used to get in there with a rope and bang it. Yeah, I don't think so. That's what I was thinking, probably pulling ropes, but I didn't see anybody go in or come out of the tower, so I don't know. Unless they're just chilling in there. I'm getting a little chilly, actually. Put my sweater on. Ooh. Oh dang, it might be the first day in a while that I don't get a conversation. If I don't get one in the next. Yeah, if I don't get a conversation by 1:30, I'm gonna call it a little short today. Yeah, it does sound antique. Yeah, I think it's more, it's like a modern one though. Yeah. Oof. For those of you who haven't seen this, it's a structure I made using popsicle sticks and basically string. So it's called a tensegrity structure. And the way it works is this top piece here is actually hanging. And the way it hangs is with this middle piece here, you know. So this piece right here at this point is actually holding this whole piece on top up. But if it wasn't for these strings on the sides, this would just be tilting, you know, would just fall in, you know, in whatever direction, you know, goes. But because we have these strings here on each corner, those keep it stable from tipping over to the side. So even though it's hanging, even though it's on top, it's being balanced by these strings, you know, on the sides, you know. So it's all tension, you know, basically that's keeping this together, you know. And then you could put, you know, it holds weight too, which is cool. So I have the level like this, and I have it on the table like this. You know, look at that. Literally just being held by the rope. I think that's pretty cool. Like, I understand how this thing works, but it still trips me out. Like, it's a trip. Like, you know, I'm obsessed with this, like, how this works, right? It's pretty cool, you know. You know, all you need is popsicle sticks, some glue, and string. You can make one of these, you know. Yeah, some tenzigrity tables. Yeah, they have chairs too, so you can make a bigger version of it, and you can actually sit on it. You know, and again, it's all being just held by the tension of the ropes. You actually want a strong enough rope to hold your weight though at that point. But yeah, it's pretty cool. Thought it'd be cool to like have it with the level on it, right? You know, here on the table, just kind of like a conversation starter too. You know. Another quick thing about this structure, you know, when you're holding it like this, the tension again is in this rope here in the center, and these are just there to balance because the pressure's coming from below up, right? But when you hold it from these, now the pressure's not coming from below up, it's coming from this up. What happens is the tension switches from the center string to the sides. So now the tension's in the sides now, you know, when you're holding it from the top one. But when you hold it from the bottom one, the tension switches to this, to the middle one, you know. So I think that's interesting, you know. I mean, there is students walking by, but no, none seem interested. No, yeah, it is one man. Yep. How long? How long did it take me to make? Well, the glue that I used didn't dry quick, so I kind of like glued it and I let it dry overnight. But to be honest, like if you have a good glue that dries quick, you know, once you have the structure made, you know, to put the strings, you got to be able to drill holes. Well, I mean, depending how you make it, you could just glue as well for the strings. But it took me like, I mean, if I'm just adding the work, not the waiting in between, it's like 20 minutes less than 20 minutes, I would say. Like 15 minutes probably to make it. Yeah, I just had to wait till the glue dry, so I kind of left it overnight, and then after I put it together. But yeah. Yeah, the thing is that I can't really put it in my backpack, so I can't really have like a big one, you know. I don't want to, you know, add to more of the stuff that I already have to carry. As it is like this, I could easily carry it, you know, it's not that big. I carried it on my hand actually when I brought it with the dolly. When I brought everything with the dolly, I just had it on my hand because it could easily break, you know. It's very fragile. So yeah, no, transporting it, it's not easy. Yeah, if I put it in my backpack, that shit would just get crushed. Right? Stick it to one of the, on top of the hat. Yeah, for those of you that joined late, I was, you know, if I do get a conversation, I was gonna bring back the trick question, but I wasn't gonna ask it first. So I'm gonna ask the number one question first, the upside down, then the water level, and then the third question is gonna be the trick question, you know. And I'm gonna use the globe images, right? And I'm basically gonna say that one of them is a photograph and one of them is CGI, right? And that's gonna be the trick question, basically. So I did wanted to try it out, but I still haven't had the chance. Nobody has stopped yet, but yeah, it'd be interesting to see, you know, how people react to that. And I think it's a good way to introduce the subject like this as well, because before I even get to ask them what their number one proof is, I'm basically gonna destroy the claim that photographs of the earth basically exist, but you know, obviously they don't. So I'm basically gonna like introduce that part of the subject, that images or photographs of the earth from outer space don't exist. So when I do, you know, come around to asking them, like, what's the number one proof, you know, that makes you believe, because that's usually the number one proof for most people is images, you know, of the earth. But again, if we could get that out of the way in one of the questions, then it'll be interesting to see or to hear what will be the number one proof, you know, that convinces people, you know, once images are out of the question, you know. So I think it's gonna be good in that sense, you know. We might be able to hear different proofs, not just images, you know. Hey, what's up, man?
How you doing?
Doing good. You want to give this a shot?
Okay.
Yeah, so I have 3 very easy questions, and I want to see if you could get 2 of 3.
I don't think I can get any, but okay.
No, you will. It's very easy. So when we have air, they actually have to do with the orientation of water.
Okay.
So when we have air and water in a bottle like this, and the bottle's at rest, the water will always go down and push the air to the top. Again, regardless of the orientation of the bottle, water will always go down and push the air to the top. You know, that's a fact. So since we understand that fact about how water behaves when it's at rest, right? I'm showing you these 2. Which one of these 2 water bottles is not in the correct orientation? 1 or 2?
2.
You got it, yeah. So why would you say number 2?
Well, the water
is on top, right?
Yeah.
That defies physics, right? So
yeah.
I actually took it like this.
Yeah.
Yeah, you're right. You got it. So that's you
I
already got
thought there
one.
was maybe a trick with the coloring, so that's why I was taking my
I
time.
usually no. That's a good thing. The water is blue. I painted it with food coloring.
So it's more apparent.
Yeah, so it's more apparent, exactly.
Okay.
So no, yeah, you got it. Even without the water, you know. Now, another thing about water, again, regardless of the orientation, water always finds its level. You know, that's a you know, physics of water. So another word, what could be another word for level? We had to use a different word. When something's leveled out, you know, that's a good one. Horizontal will be the one word definition. You know, because you could have a straight line that's on a slope, it's not level. You know, it has to be a horizontal straight line, and that's what level. So since we understand, again, water always finds its level, especially when it's at rest. So which one of these 2 represents level as we know it when it comes to the water?
On our scale?
Yeah.
This one.
Yeah, like if we went to a giant lake that was at rest, right? The body of water was at rest.
Okay.
Yeah. A, right? That's the obvious one, right?
If it's not too giant, yes.
Okay. All right, so now, so you got this one, right? Water level. So this last one is like the hardest one, but we'll see how you do. So I have 2 images here, and the reason I call them images is because one of them's a photograph and one of them's a painting.
Oh,
Well,
okay.
actually, it's CGI, so it's a
Okay.
computer-generated image, and one of them's a photograph. So I want to see if you could tell which one is the photograph.
Oh, this is the photograph.
You think it's a photograph?
Yeah.
It was actually a trick question.
Ah.
They're both CGI. Yeah.
Too big?
Well, right? Well, here's the thing. There is 3 reasons. I don't expect people to get this one, obviously, because it's a trick question. But
Maybe I
there
should have taken my time.
right? So there is 3 reasons why I asked this question, though. The first reason is just believing someone opens the door to being deceived, right? So it's not
Yes,
good to
yeah.
just believe someone, right? So the second reason is if we want to determine something is real, an image is not good enough. Because I could show you an image of me flying, but would you believe I could fly?
Sure, no.
All right. Especially if the image defies physics, right?
Yeah.
So the third reason why I'm doing this is because these images actually defy physics. You want to know how these defy physics?
I do want to know.
Okay.
Can I have 1 second to think about it before you tell me?
Sure.
Okay, go ahead.
Okay, so the reason why these images defy physics is because NASA, these are official NASA images, by the way. This one's from 2002 and this one's from 2012. But again, they call them images because they're not photographs. They make them in a computer. And the reason why, again, is because these photographs from the Earth don't exist. And the main reason is because the Earth is not a ball. So NASA claims to have satellites orbiting the Earth, right? So they need to know the radius of orbit. So they need to know the radius of the Earth that they're supposedly going around it. So they do tell us the radius is 3,159 miles, which gives us a circumference of 24,101, which means there has to be curvature every mile. And every mile has to increase because they're saying it's a curve, not a slope. So in the first mile, there's an 8-inch drop. Second mile, 32 inches, and by the third mile, there should be 6 feet of curvature. So again, if we go to
Going
physics,
from north to
from the
equator?
starting point, straight out, basically, if we're
I
measuring
see.
straight out from, because we're supposedly always on top of the ball, right?
Okay.
That's what they claim, right? So if we were to measure, straight out, then the water, especially, a lake, if we went to measure a lake, that water should be bending at the rate they're telling us. So again, if we went to a giant lake to physically measure for this curvature, the water is going to show us the physics of water. It's going to show us that it's going to be level.
If it's small enough, yes.
So you believe that in a larger, so a lake that was 5 miles across, for example, you believe that the surface of that lake is bending?
I don't know what the minimum distance one would have to be able to measure
1 mile.
But large enough, yes, it would necessarily curve.
So you think in 3 miles there's 6 feet of curvature?
I don't know what the numbers are.
Well, that's why I'm here to show the numbers. These are the official NASA
Yes, but
numbers.
you've already proven to me I shouldn't believe you.
Oh, exactly. Don't believe me. Understand how water behaves.
Yeah,
that's the thing. They could claim that the Earth is twice this size, right? Half of this curvature should still be there. You could claim it's 4 times the size. Curvature should still be there. Fact is, the physics of water doesn't have a form. It only takes the shape of the container, and the surface always collapses. It always forms an equal surface. It always levels out. That's the physics of water: measurable, testable, repeatable. There's a reason. Have you heard of the term sea level?
Yes.
How they describe the oceans?
Yeah.
Right. That's how we measure height and depth to be congruent with each other. That wouldn't work if we're measuring from a curve. Everything, all the blueprints, for example, in engineering that people use to construct railroads, bridges, they're all basically don't take account of Earth's curvature. All the blueprints are basically done from a datum line.
Yeah.
Basically. But that wouldn't be the case if the Earth was a globe. Those calculations will have to be taken into effect, especially when building bridges that are miles across, but they don't. So all the blueprints show that there's no curvature as well. All the plans, engineering, construction.
Well, I think that one assumption you have is that they're measuring, if they're building a bridge, they're measuring up from sea level.
Yeah, my point is that the blueprints, the plans that they don't take account of Earth's curvature. They actually assume is a level plane. They actually use Euclidean plane geometry.
Yeah.
They don't use non-Euclidean.
Yeah. Because we don't make bridges that are traversing this huge distance where you would have to.
In China, there's a 100-mile long bridge.
Yeah.
So there are bridges that are miles across.
Sure.
And if we're talking miles, then we're talking feet in curvature. The more, every mile increases more and more and more because again, it's curving, right?
So let me say, I just moved here from. It's kind of hard because there's a cloud occluding it.
Right.
But Oregon, down to Southern California or something here is 1,000 miles.
Sure.
It was 980 or something on my speedometer.
Sure.
Okay.
Sure.
So 100 miles is a teeny little thing.
Well, let's look at how much based on the radius they give us. 100 miles. Here we go. 100 miles.
You said the bridge was 100 miles?
Yeah, there's 100 miles. So 100 miles, they should be in feet. There should be 6,669 feet.
How does that work?
That's the curvature formula based on the radius of the Earth.
So just so I follow you, because the part when you talked about the curvature initially, I didn't quite follow you because it was too fast.
Okay.
So you're saying you're here,
Yeah.
and if you go out 100 miles, then you're saying the drop down here is
6,669 miles. Yeah.
Well, I would say that doesn't make sense to me.
Why doesn't it make sense?
Oh, in feet. Sorry.
Yeah,
so you're
feet.
a little over a mile you're dropping.
Yeah,
so
yeah.
100 miles, a little over.
Yeah, the miles.
I see.
Yeah. Obviously, when you put into miles, it's not so much, but when you put into feet, again, this is probably taller than. I mean, it's probably taller than this. 6,000 feet for sure.
Oh, yes.
Yeah. This is
by quite a distance.
This is like this is not even 500 feet probably.
No.
Yeah. So think about that. There should be that much curvature, over the water, but it's not there. You know what I'm saying? And again, there's lakes that are 20 miles across. Big lakes, giant lakes, the Great Lakes, right? In 20 miles, 266 feet in 20 miles. That's how much water should be bending, on a lake. But we understand. At least me, I understand the physics of water. Again, it doesn't matter the size of the container. Water always has to be contained, and the surface is always going to form a level surface.
Well,
that's the physics of water, basically.
How shall I say this? You've taken calculus.
Oh, sure. Yeah,
Yes?
I understand math. I mean, what do you
Okay.
Sure.
So you understand that we use each point as a flat on a curvature.
Okay.
When
you're
calculating.
When you're building locally, I get that. Yeah.
Yeah,
But when
yeah.
you're building at a distance, though. That's
So
different.
then, for the size of the Earth,
Right.
this is essentially a point.
Yeah.
Right?
I agree.
So it's going to appear flat to us.
Okay.
Right?
Sure. So let's say so you're saying that the whole lake is one big point, like a 20.
No.
So there should be deviations on that lake, then, right?
There should be a curvature if the lake is large. I don't know the number,
what I'm saying.
and I understand you have the. I'm just saying, me personally, I haven't ran the
I understand
calculations.
you.
The Pacific Ocean should have a curvature.
Okay. So so that lake shouldn't.
If it was large enough, I don't know how big it has to be
Okay.
before you measure.
Okay. So let me ask you this then.
So you could say that it's not,
Right.
but to be an extreme, to illustrate a point, to be artistic,
Right.
because it's not, this would maybe have a slight curvature, right? But it would be so infinitesimally small that we couldn't maybe measure it or something. You see what I'm saying?
At the distance of what, the lake, you're saying? So let's say it was a 10-mile lake across. You're saying that there might be a very small curve there, but we just can't measure it?
Well, I mean, if we say that the Pacific Ocean is curved, well, then we'd have to say a smaller thing is also curved,
Exactly.
right? Yes.
Exactly. Yeah. Okay.
Yeah.
So
Maybe I just didn't understand what you're saying.
Okay. So you basically believe that the curvature is.
I don't
there.
believe anything.
Okay.
But
so let me ask you this.
I would say the thing that has made most sense to me is that a large enough scale, you see the curvature, where a small scale you do not.
Okay. So if I was to ask you, what's the number one thing that convinces you that the Earth is a ball?
Oh, I used to live right here on the Pacific coast,
Okay.
right? I mean, literally
Sure.
on the ocean, and you can see the curvature.
The horizons. What
Yeah,
you're saying. Okay.
the ocean. You look out over the ocean; it's
Yeah.
curved. Yeah.
So I actually have images of the horizon here,
Mm-hmm.
and this is 20 miles in height. How would you describe the horizon here?
Okay, it's 20 miles in height.
Yeah.
And how wide is it here?
I actually don't know.
Because
the
it
distance.
doesn't matter the height. It matters your
This is
field
probably,
width.
honestly, this is probably like 1,000 miles, probably. Who knows? Probably 1,000 miles, roughly. It's more than 100, that's for sure. My point is, how would you
Okay.
describe the horizon geometrically, if I were to ask you that?
Well, the obvious answer is flat.
Horizontal.
Or straight.
I would
Yeah,
say
yeah,
the
yeah.
word horizon comes from the word horizontal,
yeah,
right?
okay.
So the only place you're ever going to see curvature of the Earth, and it's going to be through GoPro cameras like this. I don't know if you're familiar with the fisheye wide-angle lens. It curves horizontal lines.
Yeah.
So you're only ever going to see curvature of the Earth through fisheye lens like this, or through CGI images like this.
Well, you have a very small area here with an extreme curvature,
Yeah.
right? Obviously, we both agree that is not
exactly.
the
But they're
even
using
the
the same.
curvature.
They're using the same effect when they're very high, though.
the. Yeah, but I'm saying no effect. My eyes.
Have you seen the Red Bull jump, for example? You never seen the Red Bull
No.
jump when they did a jump from the edge of space, supposedly?
Oh, I know what you're talking about, but I don't think I watched the film.
Okay, I have a 20-second.
But I'm telling you, friend,
Sure.
that I've stood almost every day. My wife and I go walk, through our yard to the edge,
Okay.
and we'd look out, watch the sunset and stuff, and you can see a curvature.
So,
That's what I'm
you're saying that you're seeing a curvature from sea level from left to right,
Yes.
but why isn't that curvature here when we're even higher? That curvature should be more prominent the higher you go.
I don't know, because I don't know how light works with the higher levels of the atmosphere.
Okay.
No, I'm not trying to be cheap about it. I'm being real.
I understand refraction. You're talking about refraction, right?
Yeah, I don't know enough physics to be sure of my answer.
Here's
there.
another thing about the horizon that a lot of people don't know. The horizon is not a physical thing because it changes due to your height, right?
Yeah.
So,
Well, your eyes, you can't see.
For example, if I was to hold this water bottle and then just move away from you, a mile, and eventually you won't be able to see it anymore, right? Because it just reduces in size due to perspective, right?
Yeah.
The horizon is basically our limit of perspective.
Yeah.
So it's just how far we can actually see. If you elevate, you basically increase your angle of view, and you're able to see further in front of you. So when you elevate, the horizon should never rise with you or appear to rise, but it does. If it's a curve,
Well, unless you're going around.
no, but if you're just going
If you're
straight up,
going straight
but if
up,
you're just going straight up,
it
the
would be dipping, yeah.
but that never happens in reality. The horizon always rises with you. It's always in front of you, the horizon. And if it was actually curving down, when you elevate, you should look down at the horizon, but you never do.
I don't quite know what you mean when you say that it doesn't go up. I mean, if you're on the...
It doesn't appear to, like, let's say you're on top of a hill, right? On a very slight slope hill, right?
Okay.
If you're on top of a hill, when you elevate, do you think the bottom of the hill is ever going to rise in front of you?
No.
Exactly, right? So if the Earth is supposedly curving away from us, like at an ocean, when we elevate, the end of the ocean, basically, or the further we look, it should never rise in front of us if it's sloping down like a hill.
Do you mean rise in that you would be able to see more and more of it?
No, but it rises in front of you. So you're just looking straight out at the horizon. When you elevate up, the horizon should never appear to rise with you. You should look down like this. But that never happens.
It
basically.
goes like this, and you can see more.
Yeah,
and
that
more.
never happens, basically. That doesn't exist. So the Earth is just an extended plane. And again, the horizon is just how far we can see. When we elevate, we're able to see more of it. But it's just across. It's not going down like a hill. You know what I'm saying?
So, how would GPS work then?
Well, GPS is just using ground towers and cell phone towers, basically.
Okay, well, I'll say satellites then.
Yeah, so I don't know if you knew, over 97% of the communication here on Earth is done through underground and undersea cables, fiber optics.
Okay.
So that's over 90. That's the internet right there, basically. It's underwater cables. So all these satellites or signals that are coming from above, there's I don't know if you knew, Google had a project called Satelloons. Oh, so they're basically satellites but on balloons, like helium balloons.
Okay.
So NASA is actually the #1 buyer of helium, and any signals that are coming from above are literally just coming from Satelloons or high altitude drones, basically, which is basically for the military.
So I assume that you're positing then that there aren't satellite photographs from space, just from balloons.
Exactly. It's just from balloons. And again, you can't go high enough to take a picture of the entirety of the Earth.
So I assume you're saying, or you would agree, that then the famous photo in, I don't remember when in the 60s they took it, the first picture of Earth.
Yeah, the 1972 picture. Yeah.
Okay.
So that one, not only
yes, because it was after. Yes, it was after 16.
Yeah. So that actually, not only that does that image defy physics, the physics of water, but there's different ways people have debunked it. So I mean, this is not a really good way to debunk it, but people have are you familiar with the date and time website? Like you put a date, time, and it shows you the position of the sun on the Earth.
No, I didn't. But okay.
Point being is that they took that image of 1972, the exact date and time where they supposedly took the picture.
Okay.
And then basically the sun, how they took it just doesn't fit. Basically, how the sun should have been positioned on that date, on that time.
Okay.
So it basically contradicts that whole. So that's only one, but again, the physics of water is just going to show us that.
Let me ask you a question, because I think I might know where you're going.
Okay.
So this is my issue. So there's been generations of scientists, yes?
Yes.
Geographers, cartographers, atmospheric scientists, on and on and on, right?
Sure.
I mean, that have devoted their life to studying this phenomenon.
Yeah.
That does not mean it's correct, their conclusions, or to what degree it's correct.
Exactly.
That does not mean that someone outside of academia or research could not find a better model or more something that illustrates reality better.
Yeah.
I agree with all those premises. But I feel like one has to answer two questions.
Right.
One, why is it that this person who's on YouTube, for instance, not you, no offense to you, but has figured this out and all these other folks haven't? Not impossible.
Right.
But also, how has that been if it is a conspiracy, how has it been kept quiet? Because even like, if we imagine an Earth being a flat disk, which you have not said it is, I'm saying, if we imagine it so, as a sea captain, for a couple hundred years, sea captains, how would they not have known how far they traversed since the chronometer in the 1700s? So it gets to be a point where I'm like, well, how would we maintain such a
big lie, right, from people, right?
Yes. Yeah. How would that happen?
So very easy. First of all, first navigation, right? You're talking about navigation. How is it that navigators haven't figured this out, right? I don't know if you knew, navigation, especially when people navigate over sea, they use the celestial sphere, right, concept, right, when they measure angles of luminaries dipping in the horizon. So I don't know if you're familiar with nautical miles. That's used for navigation, right?
Yeah, and it's too rusty for me now.
So I'm just gonna do a quick overview of how that works. So a nautical mile is measuring the degree of angle change from the distance you travel from like a lighthouse, for example. So when we're traveling over water, when you notice a 1 degree change of height drop, right? For example, they're claiming that we're going over a curve, and that 1 degree change happens because you're going over a curve, right? The reality is, again, because we have a limit to perspective, and everything shrinks to a point. Everything shrinks to a point. That apparent drop is happening due to our eyes, basically. So the celestial sphere that we use to navigate is based on the eyeball. So because our eyeball is a sphere, obviously a ball, and because of perspective, everything shrinks to a point. The apparent drop of luminaries is based on perspective and not the curve of the Earth. A lot of navigators, they don't know that. They just believe, that Earth is a globe, so we're going over a curve. They don't really think about the.
Let me say it this way. Maybe it'll make it clear. So, if one imagined this particular model, which you have not posited, so I'm not saying you're saying this. If we imagine the North Pole in the center of a disk, Antarctica around the outside, to traverse time-wise, not even taking measurements, other than your sense of passing time, if you traverse from the southern tip of South America to South Africa, you would be taking one of the longest transits. Yes. So you would know that this is taking weeks, months, whatever it is, compared to just going a little ways. Would you? I mean, that kind of seems like common sense to me.
I agree. I would say.
So then, how would all these whalers for a couple hundred years? They never realized how far how long it took them, or merchant ships.
Right. So real quick. Again, I don't claim this is what the Earth looks like. The fact is, nobody knows the true layout of the Earth. So I would say this map is also a psyop. Because this was derived from vision, and this is just the opened up version of this, right? Literally, it's the same continents, the same basic layout, basically. But just
mapping it.
I don't agree with any of these, but I'm just gonna, because you're talking about how can we fly from here to here, right? Because it will be far opposed to on a globe, it will be short, right? That's your point. I don't know if you knew, when you take a flight from Australia to, for example, Africa or South America, I don't know if you knew, a direct flight doesn't exist. The flights always stop. Like, for example, if they go here, they always stop in North America, and the excuse is that they do that to get fuel, and then in other words, they just do a straight line on this map. On a globe, it looks like they're going up, and then they're going back down. But in reality, they're just going in a straight line across. But they have to stop here to get fuel, because obviously it's this long distance. But on a globe, they just go up and then come back down.
I haven't seen it that
direct
way.
Flight doesn't exist.
I've seen it the opposite way, where someone took a line on a sphere that whatever goes like this, and then you project it onto a two-dimensional surface, and then it seems arbitrary. It's odd.
Actually the other way around. I see. I know what you're saying. It looks arbitrary on this, and in this it's just straight lines.
So so what is you feel a more accurate model?
So I'm going to tell you the fact. So you've heard of flat Earth, obviously, right? So the Earth is not flat or a globe, and I'm going to tell you why. So people that are claiming the Earth is flat, they're also claiming that it's motionless, so it's just static, right?
Okay.
That doesn't
To try and account for the celestial
I don't
bodies?
know why, but
Okay.
that's just retarded. But the fact is that the Earth has constant motion. So I don't know if you knew gravity. They claim that a force pulls this and accelerates this towards the ground. I don't know if you knew that. That's been debunked. Have you heard of Einstein's theory of relativity?
Yes.
Yeah, right. So he acknowledged the fact that this doesn't accelerate towards the ground, or it doesn't get pulled or pushed down towards the ground, because one of the simple, I don't know if you knew how an accelerometer works. So if you have a tube with water and it has an air bubble, when you accelerate that container, basically, the bubble displaces relative to the direction of acceleration. So if you accelerate, the bubble gets pushed towards the front.
Yes, because it's
right?
less dense.
Exactly.
Yeah.
So it's all relative to motion, right? So when you accelerate this towards the ground, there's no effects of motion. So if you have an air bubble on a container and you let it go in free fall, that air bubble, not only does it should go down, but it doesn't. It just stays frozen. So basically the air bubble is showing you that this is not being accelerated down, and it's just decelerating. And the reason why is because, again, the Earth is in constant motion. So when you release this, it's no longer connected to the Earth, because it's connected right now through me and I'm connected to the Earth. But as soon as I release it, it's no longer connected to the Earth, so it loses momentum. So the biggest lie on Earth, believe it or not, objects don't accelerate down in free fall. It's the other way around. It's the Earth that's coming into contact with it. So the Earth is pressing up against us right now, and that's why you have weight.
Well, then you would not be able to have a sphere, because it would be going in all directions.
Exactly.
Okay.
You get it. You get it. You gave me chills right now because you're understanding, man.
You're
But yeah,
funny.
no. But yeah, the Earth will have to be expanding if that was the
Okay.
case. So that's the biggest lie on Earth right now, because again, even Einstein had to address that, and he came up with the bending and warping of space-time, which
yes.
basically just talks about inertial reference frames, explaining that it's the mass warping space, and that's what gives the illusion of falling.
But if everything's expanding, or you're positing only the Earth,
only the Earth is moving upwards uniformly.
so you're not saying the whole universe is expanding.
No.
in the same
What's
way.
outside of the Earth is a contained system. So if you ask me, what's outside of the container, I don't know. That's where outer space and all that it's just religion. Nobody knows.
Okay.
You know, negative pressure systems next to positive pressure systems without a solid barrier don't exist. So people claiming that outer space is basically a negative pressure next to Earth's pressure without a solid barrier, again, their explanation is that gravity, this force, again, the number one lie that objects get pulled down, that's how they explain away the whole model.
So again, you would not be able to have a sphere.
You won't be
because
able to
you
have
wouldn't
a
have the
sphere.
atmosphere.
Exactly.
So what is the shape that you imagine?
It's a level plane that's in constant motion, and it's, in my opinion, it's being contained by some physical barrier that basically keeping the air in here that gives us our pressure.
I'm sorry, so it's a little bit slower.
Yeah, so we have air pressure here, right? The reason why we have air pressure is because the air is being contained. That's what physics shows, you know. So the Earth shows us that it's in constant motion and being contained. But what's outside of the Earth, outside of this reality that we experience, I don't know. That's unknown. So that's, if you ask me, is there a way to find out what's? I don't think so, you know. So why are they lying? It could be just because. It could be many reasons, to be honest. I don't even know why they're lying, to be honest. All I know is that they are lying. You know, this place. Oh, here's the thing. This place was created. That's another thing. The first law of thermodynamics: energy cannot be created nor destroyed. It can only transform from one form to another. That proves that this place came from something else. So this creation didn't come from nothing. You know?
Is someone saying it's coming from nothing?
Big Bang, evolution. You know, that basically came from nothing. You know? So anybody trying to tell you how this place came to be, how it was created, is just a religion.
I'm now disagree with you in spirit of that claim, but I'm going to say that as far as I know, though, astrophysicists and stuff don't claim to know.
Oh yeah, they say it's a theory.
Well, no, you know, in the very beginning, I don't remember the length of time.
Okay.
But it's not that we can look in our telescope and see the Big Bang.
Okay.
Because there's no light.
Exactly.
Right?
Yeah.
So I think that there is a great level of not knowing what happened is when you go far enough back and approach the Big Bang.
Right.
So, but I also, you know, we can have what's the lower limit on the density of mass?
Right.
You know what I mean? We could have a very small structure that it would be have incredible mass.
Okay.
I'm not an astrophysicist.
Right.
Maybe there's a reason you can't.
Right.
But so that you could still have something it's not actually from nothing. I mean, what is that called? Like ex nihilo or something that's from the Bible is created from nothing.
Are you talking about kind of like CERN? You're familiar with CERN? They're kind of supposedly splitting atoms, supposedly, or trying to split atoms. Because again, like you said, supposedly splitting an atom is what caused this explosion, you know. That's a very dense.
Big Bang?
Yeah, the Big Bang. It came from a very dense point, where you're saying.
Okay, I've never read anything that they knew whether it was.
Well, that's what they theorize.
Came from.
Because obviously they have to warp the model to fit physics. Because again, like you said, nothing can come from nothing. So now they claim it is like an infinitely dense point. So everything exploded from an infinitely dense point. Which, in my opinion, that's just, you know.
I guess I'm a little simple-minded. So to me, if you can't demonstrate something. If you can't test it, I think it's a little outside the bounds of science.
Exactly.
And I'm not a. If you've seen my shirt, I'm obviously, you know. Well, why?
Okay.
Well, yeah, you're a pope now. Why? Because who says the Catholic Church gets to be the only one that make popes? I mean, it's all made up,
yeah,
right?
It is.
I'm not. I think that physics, in the extremes of cosmological or atomic particles, there gets to be a limit of what we know how to test at this point, and then beyond that, you can agree or you can believe whatever interpretation of quantum physics you want, but unless you can demonstrate it, that's just a belief.
Right. So again, that's true. So when it comes to physics, though, we could prove things to ourselves using physics. That's how we're able to build cars. You know, we could prove that, you know, expansion of gas can push a piston, and you know, we can make a car move based on that. So if we could prove that, you know, certain things in this reality, you know, with physics, for example, then surely, you know, if claims contradict those proofs, then we got to throw those claims out, especially if those claims don't have anything practical, right?
Or work on that model to build
exactly. So again, the fact that objects, you know, don't accelerate in free fall, again, to me, is like the biggest.
Yeah. Do you have any like a video of the bubble?
Dude, can I show you that?
Yeah.
It's a 2-minute video. I actually did it myself.
Not that I believe videos.
No. You can recreate this yourself. That's the thing. So here, I'll show you this video. I just uploaded it like a week ago. And it's called Buoyancy Proves the Earth is Not a Motionless Plane. So it's a 2-minute, 30-minute video.
Okay.
Check it out.
Oh.
It's like the air bubble
let me rewind it.
Okay. So this is the setup for the first of 2 buoyancy experiments I'll be doing. A water bottle as the container, and the camera mounted onto the reference frames that I'll be accelerating, which is the dolly. The reason why we have to constantly accelerate to recreate buoyancy is because we're connected to the Earth, which is already in constant motion. And in order to overcome constant motion, you need constant acceleration. As you can see, the air bubble is centered, which means the bottle is level and at rest. The air bubble will always be displaced or pushed relative to the motion of the bottle. When I accelerate the bottle, the pressure of the bottle pressing on the water creates a pressure gradient. The water is then able to push anything that's less dense, like the air bubble, in the direction of acceleration, which is what we will call buoyancy. You can't have buoyancy without a pressure gradient, and you can't have a pressure gradient without a contained system that's in motion. For the second buoyancy experiment, I have a cargo van as the container, a helium balloon, and an apple. I also have the camera mounted onto the reference frame that I'll be accelerating. As soon as I accelerate, the pressure of the van pressing on the air creates a pressure gradient, with the most dense air towards the back of acceleration and the less dense air towards the front. The air is then able to push the helium in the direction of acceleration because it's less dense. But the air cannot push the apple because it's more dense, therefore the apple remains at rest. The apple only appears to move in the opposite direction of acceleration because the camera is also moving with the reference frame. The helium balloon has true motion and the apple has apparent motion. In order for the Earth to be motionless, you need a force moving in opposite directions at the same time to be able to accelerate the apple in one direction and push the air and helium in the opposite direction without any motion of the container.
Sorry.
I also need this same force to accelerate a container without any displacement or buoyancy. In other words, you have to believe in a magical force that can accelerate a container without any pressure or buoyancy, and also be able to create pressure and buoyancy in a motionless container, which is the literal opposite of what physics shows. Physics proves that you can't have pressure and buoyancy without motion of a container, and you can't have motion of a container without pressure and buoyancy, proving that the Earth cannot be a motionless plane.
So again, when you release a helium balloon and you release an apple, only the helium balloon has true motion because it's being pushed up. I don't know if you knew buoyancy is considered an upwards push. It's a force. The apple, on the other hand, again, that's why Einstein had to address this. The apple only appears to go down because we're all in motion. Everything that's connected to the Earth is actually moving. You know?
Okay.
So when you release an object, it only appears to go down, but it's the Earth, everything that's coming up.
I understand what you're saying.
Yeah.
So if I give you all of that,
Yeah.
then, or is that what you're trying to say? That, hey, this doesn't add up, that you're not making a further claim, that is your claim.
Yeah.
That we couldn't be a sphere, because we would have to be moving
The Earth,
with...
exactly. The Earth has to push up on the air for the air to push up on helium. Or even if you have a pool, the Earth needs to be pushing up on the water so that the water can push bubbles up, which is what air bubbles. That's why air bubbles rise. So there's a force going up, measurable, basically.
I follow you. So, so imagine we're in a plane, like you're positing,
Right.
moving like this,
Straight
right?
forward, yeah.
So then you would have a pressure gradient.
That's the thing. You have to consciously accelerate to recreate the pressure gradient, because I know what you're saying. In the airplane, you're technically not connected to the Earth directly, right?
Mm-hmm.
But I don't know if you knew, the reason why airplanes have wings is because they rely on the buoyant effect.
Yeah.
So even though they're flying not connected to the Earth, but if they're flying and maintaining their level, they're still being pushed up. You know, that's how they're able to fly. So the air's still pushing up on the wings, keeping it steady. So in order to recreate buoyancy, you have to accelerate. So yeah, when you accelerate the airplane, it does create the pressure gradient. But once you're at a constant speed, then you could get up and walk around in the airplane, because the pressure gradient is not being felt anymore, because it's being overcome by the motion of the Earth, which is the push up. You know, the wings are being pushed up at the end of the day to maintain level. If you take the wings out of the airplane and you just go straight, eventually the Earth is going to come and crash into it. You need the wings to maintain.
That's not where I was going with it. So, so if you're accelerating, how do you account for? I'll say it this way. So a balloon that has helium, the way that I was taught is that you have greater pressure down here.
Yeah.
Right? And so, or you have air pressure.
Well, there's a pressure gradient on Earth.
Yeah,
you know,
so it's pushing, and because this is less dense, it's going to be squeezed up by the air, right? It's not.
So you think the air pressure is coming like this?
Well, it'd be coming in a chaotic gas system.
So
it'd be coming
if it was
from all
coming in from
directions.
300, then the balloon would just stay where it's at, and maybe it would just get a little smaller, or depending, right? But the thing is, it goes
No,
up.
not if there's a density gradient of air molecules.
That's the point. In order to have a density gradient,
Mm-hmm.
you need a container that's in motion, and that pressure from underneath creates that density gradient.
Yeah, I see what you're saying.
You can have a density gradient without a container that's in motion, basically. That's the biggest thing.
I don't have to think about what you're saying. I'm not trying to punch holes in it, which
no,
I have
no.
no problem with
Trust-
punching holes in things. No, I'm just, it's like a different way to think about it than I thought about it. So I have to kind of like let it compost through in my mind, you know?
So
but it's interesting.
No, yeah. So just before you go, one of the biggest things that globe earthers or even motionless flat earthers have to prove in order to take their claim serious about objects accelerating down is you have to recreate an experiment where you can accelerate the water bottle with the bubble without the bubble displacing. Now, could you imagine accelerating the water bottle without the bubble displacing? That doesn't exist. The bubble is always going to be displaced in the direction you accelerate the bottle. Meaning that in free fall, the bubble shows that it's not being accelerated. You know, that's why the bubble just freezes in free fall. You know? But yeah, that's one of the, you have to come up with a force. Like people say it's electromagnetism. Flat earthers like to say that. That is electromagnetism. But again, you have to use electromagnetism to grab this bottle somehow and accelerate in one direction without any displacement. You see how the water swishes? That's displacement. You know, that's showing you that it's in motion. So you have to believe that in free fall, it's just no displacement. You know, and again, the displacement is there once it crashes into the earth or appears to crash, but it's the other way around. But that's
So you're saying that, may I touch
yeah,
you
yeah,
on that?
definitely, yeah.
So you're saying that if it were accelerating, which is the standard model,
Yes.
if it were accelerating like this, the air bubble would push this way.
We would get pushed down, exactly.
But because we don't, I'm taking your word on
Yeah.
that one, because we don't
Experience that.
yeah,
that would-
that,
Yeah.
then it's not.
Then it's not, exactly.
So,
Would you like to?
no, hold on, because
sure,
I got
sure,
it
sure,
now.
sure.
How I can say it.
Okay.
So, you would agree that air's up here because this water is denser,
Yeah.
and so
It
if there was
pushes.
no
Well, there was no gravity,
that doesn't work,
everything
yeah.
would just be
So-
floating.
yeah. So, but if there is a pressure here, we
yeah.
could measure it.
We could measure it, yeah,
Yes,
exactly.
and a pressure here, we can measure that,
Yeah,
right?
exactly. We could.
And if gravity existed, we can measure that force.
Exactly. Yeah.
So, if the force of this
Yeah.
and the force of gravity, they're going to be different.
Wait, but how can that have a force if gravity is giving it the force? Because you're saying the force of this and the force of gravity, wouldn't that be the same force? Because let me show you something now. How can we prove that this has pressure? If you were to drill a hole right here,
Yes.
the water will squirt out, right? Because there's pressure, right? There's weight, right? That's being registered. Let me show you this. Look what happens in free fall when you have water squirting out. This is what happens in free fall. This one's even shorter. Just real quick, okay. So this is another experiment I did again. This is buoyancy and free fall. I slow it down so you could see. So there's a bubble rising and a nut falling. But as soon as I release it, look, the bubble rising stops. And again, it's rising, and then as soon as I release it, it stops moving. It's like decelerating, basically. Right? And this is what happens when I actually accelerate down. You're gonna see the bubble start to go down a bit. Watch. When I accelerate down, the bubble wants to go down. But I can't overcome the motion of the earth. So it just comes back up again. But you could see for that second, it goes down. Look, when I accelerate down, look at that. Boom. It wants to go down, but then it comes back up.
So,
And then this is pressure. Look, pressure with water squirting out. But as soon as I release it, look what happens. There's no more pressure. Pressure vanishes, weight vanishes, everything vanishes. There's no effects of a force. All the effects of a force vanish in free fall. So the only force that we experience is up, you know, and buoyancy being that, you know. And we can recreate buoyancy again by accelerating containers in different directions, you know. Oh. But yeah, basically physics shows us that objects don't accelerate down, basically, which means a globe would be impossible, you know. Again, you have to be growing.
so there's going to be a rate of speed at which the bubble moves
Sure.
that we could measure.
Sure.
Yeah?
I would say that rate of the bubble is a constant. You know, it doesn't accelerate, like keep accelerating. It only accelerates when it's at rest, and then it starts its motion, but then it stays at a constant rate after that. It just finds its equilibrium at that one, because it is being, again, the Earth is not accelerating, it's in a constant motion.
Well, I'll say, like, we could imagine a rocket attached to this,
Okay.
where it goes, let's say, 10,000 miles an hour,
Okay.
or something.
Sure.
Or if I just do this,
Yeah.
right? Would you say that the bubble would move at the same speed in both of those?
Oh, no,
situations?
no, it wouldn't.
Okay,
It wouldn't.
so there's a rate at which the bubble traverses that
Sure.
space, and we could measure it if we're clever.
Sure.
And there's a rate, whatever, 8 meters squared per whatever.
9.8 meters per second, that's
Yeah,
the rate.
yeah, right, of the acceleration. So I feel that those two would be involved in a relationship as far as that bubble moving or not, based on the speed at which the containers move. Does that make sense? I'm not saying it will at all.
No.
But
So the speed does affect the speed of the bubble, but what also is going to affect the speed of the bubble is the substance. So if you have like a thicker substance in here, like oil, it's going to make it move slower.
Sure.
So it depends
because it's
on,
actually force.
Yeah,
It's not speed, right?
Exactly, force. Yeah. So again, it depends on the force or the and the medium that it's surrounded by.
Sure.
So those are two variables that would depend, you know, the motion that would basically dictate the motion of the bubble again.
Yeah.
But again, you can have motion of the bubble without any motion of the container. That's the thing. You would need a magical force like that could go through the bottle and then move the water and air without moving the bottle. That force doesn't exist. you would have to claim that water's kind of like magnetized, and there's this magnet that can move water. Like, you know, it just doesn't make sense.
But so you would perhaps agree that the rate of movement of the bubble,
Yeah.
the substance in here always being the same,
Okay.
because I agree with you about the rate at which it moves is in proportion to the force
As well, yeah. Yeah.
put upon it,
I agree.
which was my speed with the rocket.
Yeah,
that
I
thing,
agree.
right? So if you take the force that the Earth is pulling on it with,
Okay.
and the force that's being placed on it by the water, right?
But
If
that's
one
the-
of those is larger than the other, does you see what I'm saying? You would get two different effects, whether moving and if it, let's say it was equal, it would not move. Does that make sense?
But before you get
Hold on,
into,
but do-
no, it makes sense because
Okay.
they cancel out. I
Yes,
get you.
yes.
But here's the thing: you're invoking two forces now. You're invoking a force that can accelerate this down.
Yes.
And now you're invoking a force that can push the water
no,
up.
the force of the
You know what I'm saying? You're claiming there's a force pushing this down, but then there's also a force pushing the water up. So it's a force going in two directions at once. That doesn't make sense. Does it only be a force going down?
well, the force pushing the water or the bubble up is not pushing the bubble up; it's pulling the water down. That's the force. So the water squeezing.
But that's the thing. If the water's being pulled down or pushed down, whatever term you want to use, then the bubble will follow that direction. You get what I'm saying? If the water's being pulled down, then the water's more dense than the air, so it should push the air down. Buoyancy goes in the direction of acceleration.
So you're saying going like this,
Yes, the air bubble
the
will go that
bubble
way.
goes like that.
You go that way, the air bubble goes that way.
Which we're having gravity affect it evenly in this direction, in this
Sure.
on
yeah.
this plane,
Yeah, yeah.
right? It's not doing this. You're not talking about.
No, yeah.
So like this, the bubble's going to move back
But
and
that's-
forth because we have gravity being even from here to here. And so that
Right.
canceling out, we're only dealing with the force of,
left to right, and the
of
bubble
movement.
reacts to that movement, right?
And then when we're going down, right, you have it can't go here.
But it could go.
Because
If you
it-
manually accelerate, it does. That's my point. If
If
you had a
you go
machine,
like this,
if you had a machine
yeah.
and you put it up like the height of the tree,
Mhm.
and you actually accelerate it down, you would
Yeah.
see the bubble go down.
Not because something's pulling that bubble down, but
It's being
because
pushed.
the water's
Pushing
going in
it
the
down.
opposite direction.
Exactly. Yes.
So now that water's pushing up with a certain force.
Well, it's not pushing up; it's the bottle pushing down on it. So it appears,
Okay.
the water appears. It's like when you're in a car and you accelerate, it feels like you're being pushed to the back of your
Mhm,
seat, but
mhm.
you're not being pushed to the back of your seat.
Yeah.
It's your seat being pushed against you. So that's what's happening.
Okay.
It's not the water pressing up against the bottle; it's the bottle pressing against the water.
But that force
Yeah.
that the bottle then transfers to the water,
Yes.
yes, that force, if it were equal
Okay.
to the,
But that's the thing, in free fall, there's no upward force, is what you're saying. You're trying to say that when you accelerate this down, you actually have to contradict the upward force as well, right? That's what you're saying is canceling out. But that's the thing, when you accelerate this, when you release this in free fall, again, even Einstein acknowledged it. They even claim that gravity is not even a force anymore. It's a bending and warping of space-time.
Yes.
So they claim that it's not even a force. So they acknowledge that a force requires displacement. Again, the pressure transfer. They acknowledge that, so that's why they can't call gravity a force anymore. So it's just imagination. You know, so again, what you're saying is that, oh, there's a force pulling it down, but then there's also a force pushing it cancels out. Well, there's no force going down because even the mainstream, acknowledges that. Again, this is like the biggest
well, I think there is a force
going down.
in the, well, kind of all around. Like you have the molecules, yes?
Okay.
And in a gas, they're bouncing around.
Again, I would say the air pressure we have is because Earth is being contained, not because
I know.
there's a force down.
Yeah, but in here,
Right.
inside the ball, let's just say
Sure.
this is in free fall, and you're taking a picture and you click so that we can talk about it. We
Okay,
take a
sure,
frame.
sure. We take a frame,
and
sure.
the bubble's just right there.
Right,
Right.
yeah, exactly.
I would say there is a force within that bubble, which is the force of the molecules bouncing around in a gas bubble.
Okay. So you would say that just by something
Like if I shake up a pop and it goes.
Yeah, you
right?
increase the pressure in there. Yeah, I agree. I would say that's a little different because obviously
But you have
that's a pressurized system.
It's a buoyancy. You have the interaction with the pressure of the water,
Sure.
the liquid, and the pressure of, in that case, air. I guess a submarine, it would be similar. And if you go down too far, it crushes the submarine. Yes.
I guess the main point I would say that even in that scenario, obviously air, when you know, air will always get pushed up. That in my opinion shows the direction of the force of the motion.
Yeah, I follow you, and I heard that.
Yeah.
But what I'm saying is if you have this bubble in the center,
Right.
it's not a zero pressure. It's not a.
So you're saying it's being accelerated without basically effects of pressure, basically, in free fall?
Well, I can kind of only think of it in the way I think of it, so that's why I'm trying to walk you through it. So maybe humor me.
Yeah, sure.
So if we took that snapshot and that bubble that's in the center there would have a pressure outward, right? Like if you had a vacuum and you like somehow stuck the straw in there and went like this, there would be positive pressure pushing out from the air.
I get what you're trying to say, you know, but how does that prove that?
Well, you have to take some steps with me. That's what I'm saying.
I'll accept
so,
that, sure.
Like a balloon, right? If you poke it has a greater pressure than the atmosphere.
Sure.
So if you poke a hole, the air comes out.
Sure.
Right?
Sure.
So that bubble in there isn't a void. It's not a vacuum.
No, I understand.
So you have two competing forces then when we look at that. You have the...
I would say that's surface tension.
If there's not...
Right.
If they're not accelerating, but we're underneath the water.
Right, sure.
We're underneath the water,
sure.
so it's not the surface.
Sure.
So you have the pressure of the water.
Right.
And you have the pressure of the gas inside the bubble.
Right.
And they meet there, right?
Sure.
So if you increase that liquid pressure, that bubble would shrink.
Yeah.
Right? And maybe disappear.
My thing is that in order to increase the liquid pressure, it needs to be in motion. That's
I know, but you're getting ahead of me. That's why I'm trying to step you through.
Okay, but you're saying that you have to imagine that there's pressure even though it's not moving. That's where I'm like, well, that doesn't happen in reality. That's my point. If you were to put a device that can measure the pressure inside this vessel, right? It would measure, you know.
Well, it doesn't have to. Okay.
Let's say it was a bigger bottle, right? And we could put a measuring device inside the water to measure the pressure, right? When you release that in free fall, that pressure is gonna reach zero. When in free fall, there's no pressure. That's the point. And I get what you're saying. The bubble still stays as a bubble. Why doesn't it, like, you know, mix into the water, right? I don't know what you're trying to say, but the fact is there's no pressure in free fall. That's what physics shows us, you know.
So if we took a balloon that floated here, okay, because I'm trying not to transgress your view of the accelerating, and you put it in a big container that we could be airtight, and we evacuated it, so it created a vacuum, right?
Okay, the
what would that balloon do?
Expand.
Yes. Yeah. So then that shows you that there is pressure inside that balloon.
What's happening there is when you remove the air, gas pressure. One of the laws of gas pressure, again, the second law of thermodynamics, is it always wants to equilibrate. Gas always equilibrates. So in order to maintain two opposing pressure systems, you need a solid barrier, right? So based on understanding that gas always equilibrates, when you create a vacuum with a balloon inside, naturally it's gonna expand because the gas wants to equilibrate.
Yeah, it wants to expand.
Exactly.
Yeah.
That's just the natural. That's just how gases behave.
So that bubble in there, it wants to expand.
That's the thing. I don't know where you're getting that.
But you just said that it wanted to expand.
But that's in a vacuum. This is not a vacuum.
Okay.
Yeah.
So but you said gas always wants to equilibrate.
Yeah, equilibrate.
So if we had a huge column here, like we have a bubble in there, and then we have this huge column, and we put a lot more water on it, would that bubble change shape or size?
No, it would just go up. If you have a column with water and you put a bubble, it would just go up.
Poor model. So if you have, the submarine measures pressure as it goes down in depth, yes?
Yeah.
So then why is there greater pressure on the submarine at a lower level, right? The submarine's full of gas.
It's actually very simple. You want to know why there's lower pressure underneath? It's the same reason why we have a higher pressure gradient on the surface of the earth than on a mountain, is because if I was to stack bricks right here, for example, right, 10 bricks, and I put a scale underneath the bottom brick, and I put a scale halfway and another scale on top of the last brick, which one's going to read more pressure?
Of course, the bottom one.
Why?
Yeah.
Why?
Well,
because there's more mass
there's
above.
more mass.
Exactly.
Yes.
So that's the same principle as when it comes to the ocean and the air.
Yeah. So the water has more mass than that bubble in the center.
Yeah.
Yes.
No. Well, okay, so the reason why there's more pressure red underneath than up here is because there's more mass above.
Yeah.
So what does that have to do with the air bubble? That's what I'm trying to get. But again, in free fall, all of that becomes irrelevant. There's no pressure gradient.
I've heard you. Yeah, I heard that. So I keep talking about the bubble in the center because remember I took that frame out. So because you're claiming that bubble's not moving.
Yeah.
So then I'm like, okay, let's talk about that.
Yeah, sure.
Okay. So in that instant of time or whatever, right?
Yeah.
There is evidently an equilibrium of pressure as far as movement.
I would say that's just the vanishing of pressure. You're interpreting it as equilibrium, and and the way I see it is just there's no pressure.
But if we move it horizontal, then there's this movement of the bottle.
Right, exactly. So let me just the experiment that I showed you. I moved the water bottle. When I pushed it, I literally probably didn't even go faster than 5 miles an hour.
Yeah.
And then the bubble moved.
Doesn't take much.
Quick.
Yeah.
Do you know how fast they claim this accelerates down?
At the whatever.
In 2 seconds,
Yeah.
it's 88 miles an hour. In 2 seconds. That's faster than a Tesla. That's the claim. That's 9.8 meters per second squared.
Yeah.
Meaning in 3 seconds, I'm supposed to believe that this is accelerating towards the ground by over 350 miles an hour without any displacement of the bubble. That's ridiculous. You know what I'm saying? If we drop this bottle from any height, the bubble will never get pushed to the ground. And again, it's because people will say, oh, but if I release this here, it's a small impact. And the higher I release it, there's a bigger impact. So it's an acceleration, right? The fact is, it's a deceleration that's happening. So again, if this is going 1,000 miles an hour with the Earth, hypothetically, as soon as I release it, there's a deceleration that happens. So the more time it has to decelerate, the bigger the impact is going to be.
So you could do it. Is the bubble staying not moving invariant to how far the free fall is? Do you understand what I'm asking?
I get what you're saying. So yeah, it would just stay still.
No matter if it drops for a mile.
Some people claim that after 5 seconds the bubble.
Well, I don't know. Yeah.
No. Some people claim that, but I just think that's funny. But some people do claim, oh, you have to drop it from 5 seconds, you know, and then the bubble's gonna start moving, you know, and it's like, I think at 5 seconds you will have to drop it from like a really tall building, like a
sure,
really,
but it hasn't been. I mean,
that test hasn't.
You can drop it from a balloon with a camera attached to it. You can see, but science has not done this.
No, and they actually avoided. They actually recreated their whole. Well, that's the whole reason why Einstein had to come up with his theory to acknowledge the fact that doesn't happen. That's why Einstein came. And I don't know if you knew, but the mass attracting mass theory of Newton's theory, they don't even use that anymore. Basically, it's just. It's again, that's why they use the modern theory of relativity now, because they acknowledge that fact. You know.
I just wanted to see what you were all about.
No, yeah. So here, I could give you the flyer.
Sure.
Yeah.
Well, it's been interesting talking to you, and I appreciate.
Yeah,
you
take care.
Well, I'll think about what you had to say.
Yeah, definitely, man. I appreciate the talk, man. Yeah. Okay, so let's get started.
Yeah.
I have everything here already, but we'll start with the easy one. So it's 3 very easy questions, and I want to see if you guys could get 2 of 3.
Sure.
So the first one has to do with they have to do with the orientation of water, both. And when we have air and water in a bottle like this, and it's at rest, could we agree that the water always goes down and pushes the air to the top?
Sure.
Regardless of the orientation, right? That's just what water does, you know, it goes down and pushes the air to the top, especially when it's at rest. You know,
every liquid does that.
Yes, since we understand the effect of water, I painted the water blue with food coloring just to make it easier to see. But since we understand that fact about water, which one of these 2 water bottles is not in the correct orientation?
Well, what's correct for a water bottle? But like this would be right side up, and then this would be like upside down.
You got it, yeah. And obviously, what made you say that?
But the water's.
Obviously, the water, right? It's very obvious, right? It's very easy. No, yeah, I took it like that.
Yeah.
You got it, yeah. So this second one is pretty easy as well. Another thing about water is that, again, regardless of the orientation, it always finds its level. You know, water doesn't have a form, you know. It just always finds its level, you know. So,
property of liquids.
Exactly, yeah, there you go. So since we understand the effect about water as well, which one of these 2, again, it's a body of water that's at rest. Which one of these 2 represents level as we know it when it comes to the water?
Context dependent.
Okay, let's say we're in a lake that was miles across and the lake's at rest.
Okay.
Which one represents level as we know it?
I wouldn't know the exact maths of it, but either one could be correct. I don't know how big the lake would have to be.
Okay, let's say it's 5 miles across.
I don't know how big the lake would have to be.
Okay, so
but like an ocean would follow these rules.
Okay.
So whereas like a lake would follow these rules.
Okay. Okay. So you think it's both, basically?
Yeah.
Okay.
It depends. It's contextual.
Okay. Fair enough. Okay, so this last one. Okay, we'll go back to this one, but this last one is just to test your vision. So I have two images here.
Okay.
Yeah. So, and the reason I call them images is because one of them's a photograph and one of them is CGI.
Okay.
So I want to see if you guys could tell which one's the photograph.
I mean, my instinct would be this one.
Okay.
Because
Yeah.
it looks less rendered.
Less rendered.
Yeah.
But
I think either
Okay.
of them could be.
Okay, fair enough. All right, so this one's actually a trick question. They're both CGI.
okay.
So there is three reasons why I asked this question, because I don't people expect people to get this one. But the first reason is just believing someone opens the door to being deceived, right? Because you guys believe me that one's a photograph, that influences your choice, right? So the second
Sure.
reason is if we want to determine something is real, an image is not good enough. Because if I showed you an image of me flying or me walking on water, would you believe I could do those things? No, especially if an image defies physics, right?
Sure.
You got to throw that image away. So, and then the main reason why I'm doing this is because photographs of the Earth actually don't exist. I don't know if you guys knew that.
It's too big.
Okay, so
We'd have.
so the real reason, in my opinion, photographs of the Earth don't exist is because these images actually defy physics.
So, what do you consider a photograph?
Photograph is basically it's just a snapshot, not computer generated. So it's just a snapshot.
But what do you consider computer generated? Like if I take 4 images with a camera and
That's
then use a
computer generated.
computer to stitch them together?
Yeah, that's computer
Well, there
generated.
goes your whole thesis.
I know. But
Okay, so just real quick, so I'm going to
Yeah.
tell you how these defy physics, right? Because again, we understand how water behaves and
Sure.
the surface always finds its level. So NASA claimed to have satellites orbiting the Earth. So they need to know the radius of orbit. So they need to know the radius of the Earth that they're supposedly going around it. So they do tell us the radius is 3,959 miles, which means there has to be curvature every mile, and every mile it has to increase. So in the first mile, there's an 8-inch drop. Second mile, 32 inches, and by the third mile, it should be 6 feet of curvature.
Yeah.
So if we went out to a giant lake that was miles across, again, 3 miles is all we need. The lake is going to show us that it's going to be parallel or level to anything horizontal above it, but they're trying to tell us that that lake is bending 6 feet in 3 miles and increasing more and more. So 66 feet in 10 miles. So this will be the #1 experiment to debunk the globe of physical measurement of the Earth, water in specific, water
Okay.
being level, right? So if I was to ask you guys respectfully, what will be the #1 proof that makes you believe that the Earth is a ball?
Other than just like that's how physics works.
So what about physics tells you that the Earth is a ball?
Well, so we can observe other celestial bodies,
Okay, so looking at the stars, right? Okay.
stars,
Or
planets.
lights, yeah, sure, whatever you want to call them.
The moon.
Yeah. So we can.
So I would say that's kind of an assumption, right? Because if you just look at lights in the sky and then just assume that Earth must be a sphere, because
No, we can quantitatively measure
okay,
it.
how would you quantify the ball
Yeah,
Earth?
we can quantify the rotations of all of the planets.
No, I'm talking about the Earth being a curved surface or a ball. How would you
Right,
You
quantify
can
that?
quantify the rotation of the Earth.
Or how would you quantify the rotation of the Earth? if I
Well,
may
you're
ask?
like.
Do you know the speed of the rotation of the Earth that they claim, by the way?
Not offhand.
Okay, it's 1,067 miles per hour.
Okay.
So that's faster than the speed of sound, which
Sure.
it's just, by the way, it's going in one direction. So if you were to fly, with the spin of the Earth, technically you should be moving faster than if you were flying against the spin of the Earth, right? Or vice versa. I'm sorry, But the fact is, when you fly from here to New York and New York to LA, it's the same distance, 3 hours.
Well, there's
It's the same
wind
distance,
speed.
but
it's the same
different time.
No, it's the same time.
No, it's not. I fly to New York all the time.
So it takes double, you would say, the time?
Well, there's
It
wind
depends on
involved,
tailwinds.
too.
Yeah. But like flying to Charleston, which I do, takes roughly like 6 hours. But then flying back, it takes less time.
Okay. Yeah. So, again, I will go to physics. Again, how water behaves. It's just going to show us whether the Earth is bending or not.
But
So-
yeah, okay. So now I understand. I was wondering what your
this was about?
ideas were. Yeah.
Yeah.
So I just wondered, like, if you see other things being created in the universe where you don't see them because it's on timescales that we can't really see like that. But if the other planets are spherical, why would Earth be different?
I'll tell you why. Because in my opinion, Earth is a creation. So what's above, the lights in the sky, are basically just that, lights. So nobody knows what exactly they are. All we know is that they're constant. That's what we call them, constellation.
Yeah.
So the stars reset every night, every year, right? They rotate above. And that's why, the word constellation comes from, because they're constant. If we were truly shooting through space in 6 different directions, over 1 million miles an hour, then the sky wouldn't be a constant. It would just be a different sky every night.
But it's
It will be
not
parallax.
a
There will be
constant.
parallax.
It is different.
There is parallax.
There's no parallax in the stars. You should look that up. Yeah. Yeah, the stars reset every year. That's why they're called constellations.
That's
They're
not even
constant.
how far they are, though. How far away they are.
Well, that's the thing. Nobody actually knows the exact distance to the stars, but I would say they're very
Well, I
local.
mean, it's hard to have a ruler that's 300 light years
Exactly.
across.
They claim
but
to use lasers, obviously, and
Sure.
bounce things off, supposedly. off.
Well, isn't it also like my night sky is different than the night sky
Oh, yeah.
in Australia?
Yeah, I agree.
Right?
Yeah.
And it has to do with
So
just
why is-
perspective, yeah. So, because the sky is
So-
very close to the Earth, it's not like light years away like you guys
So
think.
you think like pancake,
I guess
flat,
that's like
and
the...
then a globe
so
over.
So I don't know the dimensions.
Dome over top?
No. So I don't know the dimensions of the Earth. So it could be circular, like people claim, but I honestly don't know. But for sure, I know it's level. As far as a container, how does it look? I don't know. But if you ask me, second law of thermodynamics, you can't have a high pressure next to a low pressure without a solid barrier. So the fact that we have pressure here on Earth and they claim outer space is negative pressure, you can't have them coexisting next to each other without a solid barrier. So the Earth is a contained system, and the stars, if you ask me, are part of that. And
then how does air work?
what do you mean?
Like weather, like high pressure, low pressure
so
systems.
Yeah, so when it comes to that, obviously that's separate from the physics of the dimensions of the Earth. When you're talking about weather and stuff like that, I would say that's a separate subject, But honestly, well, obviously the motion of the sun creates weather patterns and stuff like that, I would assume,
So we're in like a container.
Yes.
There are edges.
That's the thing.
So like if a hurricane is moving and it like moves across areas of land,
Sure.
ocean, does it just hit the edge at some point?
No. So the edge, if we are in a container, in my opinion, we are. The outer circumference of the Earth, I don't know if you knew, there's an Antarctic treaty. So it prevents any civilians like myself. If I was a millionaire and I've had a boat or a plane, I cannot independently explore south. So if there was an edge, or I would say the end of the containment, we're not allowed to go that far to see if that actually is the case.
But
it's
people
illegal.
still go to Antarctica.
Oh yeah, but it's all through expedition. Basically, you have to pay like $20,000 and basically hold your hand. You can't independently go off away from the group.
Well, probably because you eat him.
Well, that's what they say. They say they do it for protecting us. But again, if you ask me, it's because they don't want us to find out what this place actually
So
is.
you don't know the exact shape.
No.
But it's flat and there's ice.
I would say it's
around everything.
I would say it's level, and flat is a misrepresentation, and I'm gonna tell you why real quick. Flat has nothing to do with orientation. So I could have a flat piece of paper like this, right? But if it's in a slant like this, it's not level, right? The Earth is level. So the Earth has orientation, and in order for something to have orientation, there needs to be motion. So the Earth is actually moving up against us right now. So when you release an object, it's not the object that accelerates down, it's that the Earth comes up to it, basically, to move. So objects
we're
decelerate.
Just constantly moving up.
Not up in a straight line, but I don't know the exact movement of the Earth. But it is in motion.
So the universe is infinite?
No, that's the thing. I don't know what's outside of the Earth. Nobody knows. I would say
whatever's outside of the Earth is infinite. Because how would we keep moving up?
that's the thing. You're familiar with the high tides, right? The tides, ocean tides.
Yeah,
No,
sure.
that's actually a horizontal movement of water. You could look it up. So that, to me, shows me that the Earth is not moving in a straight line, because the ocean water is deviating and water is level perpendicular to the vertical, which is the motion. So the fact that the ocean tides are showing declination, deviation, shows that the Earth is not moving in a straight line. So the Earth, in my opinion, is part of a cycle. So it's not moving through infinite space. A lot of people like to use that as a red herring, or like a straw man argument, I'm sorry. But I don't claim that, Again, the ocean tides, in my opinion, show us that the Earth is moving not in a straight line.
So like this.
I would
But
say maybe
always upwards.
No. It's probably in some kind of track doing circles, for all we know. But it's pressing
like
up.
this.
It's only moving up relative to us within it. Yeah,
Like this.
yeah. Have you ever seen a centrifuge?
Yeah.
Yeah. So I wouldn't say exactly like that, but that's just an explanation, to create
But
orientation.
wouldn't that create an outward pressure.
Yeah, exactly. That's what I'm saying. I don't think it's exactly like that, but it's moving not in a straight line. So I don't know.
So the Earth is like tilted like this and going in a centrifuge, and that's how gravity.
Well, gravity is the pressure of the Earth's motion. So it's not a pulling force that they claim in the mainstream. You know?
Yeah, but the force has to come from somewhere.
Yeah. So whatever.
So the force comes from a centrifuge.
No. I was just using that as an example of how you could recreate orientation.
We have centrifuges. We
Well,
use them all the time.
Okay, sure.
The pressure goes like the.
Yeah, it goes outward.
Out.
Yeah. That's a bad example. That's a bad example. Only use that to show that you could recreate orientation based on a rotation. The exact motion of the Earth, I don't know. That's the thing. But it's not moving in a straight line.
Potentially flipping.
I mean, if you're outside of the Earth,
And
I don't know. It could be.
Gravity's pulling. You said it's not pulling.
It's not pulling. It's when you release an object, the object's not being accelerated down. It's just losing momentum. So if again, hypothetically, if the Earth right now were in motion at 1,000 miles an hour steady, right? Since I'm connected to the Earth, I can feel the pressure from underneath. I'm moving with the Earth as well, right? I'm holding this, so technically this is moving with the Earth as well. As soon as I release it, it starts to lose that momentum. So it starts to decelerate. So it's the motion of the Earth that gives us the apparent direction of gravity.
I just don't know how you would get that motion.
What do you mean?
Because you said that we'd have to be going up.
Oh yeah, so the motion of the Earth, a lot of people say, well, what's causing the Earth to move, right? Well, that's part of the creation. Whatever the prime mover is what put the Earth into. Whatever created this place is what put it into motion as well. So this place is 100% a creation.
But then wherever we're moving within has to be infinite. Because you have to keep going.
That's
up.
the thing. It could be, but I don't know what that is. If it is, it could be water. Some people claim it outside of the Earth is just infinite water. Some people claim.
But there's no way to prove that.
I know, exactly. There's no way to prove any claims of what's outside of the Earth. But the globe Earth makes a lot of claims, and a lot of people believe it about other space balls. And
I feel like the claims that they're making have a lot more backing.
I would ask what backings do they have, because all they do is look at things and they make up stories about it and claim to have satellites in space. But
you said they look at things and make up stories about it.
Yeah, to fit their presupposed model, which is that the Earth is a ball.
Okay, but how do we classify anything on Earth?
Again,
we're looking at things and then.
Yeah, but just looking at things in the sky is not going to tell you nothing about how the Earth.
Yeah, but we've been to space.
Well, I would say that's a belief. You believe astronauts have gone to space, right?
Yeah.
I would say that astronauts are 100% lying. So the people
all
that
of them?
Yeah, all the astronauts
from multiple
are lying.
countries.
Yep.
We can't even come together to change daylight savings.
That's what I say.
Within
But
this country,
exactly.
But you think several countries, including Russia.
I don't know if you knew Russia and the U.S.
And
share the
us.
space station. I don't know if you knew that. The ISS.
Yeah, we do.
So I think that's a bit of a contradiction of what you're saying too.
Yeah.
Yeah. So we're at war here on Earth, but in space we're all buddies.
What is their motive?
Motive is to control. Is to keep people ignorant and no offense, but keep people dumb.
How does space affect? How does believing in like the moon landing control me?
It's not about believing in the moon landing. It's believing something that contradicts our daily lives, like the physics of water. So if you could believe water bends when in reality it doesn't, and basically, we could prove that to ourselves every day. If they could get you to believe in something contrary to something that's very simple, then they're gonna get you to believe in anything else, like the economy, for example. I don't know if you knew, but the economy has no true value. Like the dollar doesn't have real value.
Yeah.
So it's just faith-based.
I would say that's a much more direct way of controlling.
Yeah, exactly. So it's about dumbing people down when
But I don't think that controlling my knowledge about space is controlling me directly.
It leads to because when you accept this, you basically place trust in the scientists, right? You trust them, you believe them, right? That's why you believe it, right? Mm-hmm. So now this belief goes on into other subjects like the economy. And now,
so why believe any science at all?
That's the thing, you shouldn't believe science. Science is the method to prove things so that you don't have to believe. So I go with what I know, which is the physics of water.
So if you go to the doctor and you get a medication,
I would say that's a bit different, but because I'm actually vegan, so I take care of my own health myself. So
I'm vegan too.
Okay,
but I'm diabetic, so if I didn't have insulin, I'd die.
Well, I would say I don't know if you knew, but raw vegan lifestyle, plant-based, whole foods, plant-based, basically cures if not all diseases.
Dude,
and there's a lot of studies on that.
Okay, I think you've lost me at this point.
Okay, well let's go back.
I'm diabetic and I can't cure it.
Okay, well let's go.
I have autoimmune cells.
Okay, well, let's
that
go back
have
to the
attacked
physics
my
of
other
the
cells.
world, because when it comes to health, I would say that's a completely separate subject. And
Well,
again,
I feel like you're pushing a different method of controlling people by not. You're deciding to not believe in any science.
no, I believe in the science that I can prove to myself. That's measurable, testable, and repeatable.
But that's not feasible because
Okay.
we have.
If-
Like,
if- if
we're
sci-
scientists,
okay,
and
if-
we have to believe each other.
So what is the scientific method, if I may ask you? Yeah, what's
I
the
think we
scientific
have-
method?
Do we have to go?
No, we can. They're growing pretty slow. We can stay for a little bit.
I mean,
you have to come up with
but-
a question, and then you test your question.
how do you
Yeah.
test it?
It
You have to show a demonstration, right?
depends what kind of
You
science
plan
you're
an
doing.
experiment.
Well, let's say-
Yeah.
experiment, and then you have to analyze the data, and
Okay.
then whatever the data says.
And you have to, like, the way you analyze the data is also important.
Right.
So,
So-
like, we'll do, like, a lab meeting where we
Okay.
talk about other people's data and
Okay.
whether or not we believe
So this
it.
data that we're getting from NASA, the radius of the Earth, right?
Sure.
So we say, you guys can look it up right now, so you don't think I'm making this radius up. Based on the radius, based on the data that we're given, right? This is the curvature formula based on the radius. Based on the data that we're given, if we were to put it to the test, like measure a giant lake again that was miles across, do you think this will be a viable experiment to physically measure for this curvature? Or do you think there's a better experiment?
Well, what do you mean? So we have an idea, but how would you test it?
Yeah, so the claim is that
Yeah.
water bends
Yeah.
8 inches per mile squared.
Okay.
Right? We have a lake that I say the lake is level, not curving. But let's say we have that lake and it's 5 miles across, right? We can easily build a level structure over it. Basically, essentially like a giant ruler, right?
Sure.
So we'll start from the plumb line. That will be our starting point, and we build outward. So we make sure we stay level relative to the initial plumb line, right? So the horizontal structure stays level.
Relative to the water surface?
No,
or
relative to the plumb line.
bottom of the
relative
lake?
to the initial plumb line.
Okay.
That's
Well,
what.
what's the plumb line
You know what?
based on?
Well, a plumb line. I don't know if you knew when you hold a weight in a string, the plumb line is the true vertical.
Okay.
So it's the
Okay.
vertical. It's the perpendicular to the level.
Yeah.
So we'll start from the first plumb line and build perpendicular to that plumb line. The water then should start bending if the Earth is a ball.
Sure.
The water should start bending, increasing more every mile. So in 3 miles, there should be a 6 feet deviation. So if we start at 5 feet, that gap should increase to 11 feet. But
Sure.
we understand physics of water, it doesn't do that.
But
The
you're
water
not
always.
going to build a level structure for 3 miles.
Why not?
It's not very practical.
You don't think so? You don't think we have the technology to do that?
I think we could.
Then
I don't.
could you think of a better experiment? Because I know in the mainstream, like the Netflix documentary, I don't know if you guys seen it, they
Yeah.
focus on, that's a mockumentary by the way, but they focus on laser experiments with that. At the end of the day, those are inconclusive because there's refraction, there's, light, acts in different ways,
How
But
do
there's
you-
also waves. So how do
Yeah.
you
No,
control for
a lake-
water level?
Lake. It has to be at rest. A lake. Because I know on the
lakes
oceans,
have waves.
Lakes have waves.
I mean, on a very calm day, maybe very slight waves, but
Also, what about wind?
Yeah, I mean, like,
even if
you could probably get like a 6 to 8 inch wave in a lake.
Yeah.
I mean, even if there was a wave, the overall levelness of the water is still the same.
Well, but
even
you
if
have
there
it
is a
in
wave.
a wave, so you've got peaks and troughs. So
Right.
that's a difference of 16 inches. That's
Also,
over a foot.
How do you decide?
How do you? What about 6
data-
feet in 3 miles? You think there's a wave 6 feet
Sure.
in a lake?
Yeah.
No, and it wouldn't be 6 feet, but like it would skew
I mean, it
your
depends what lake.
measurements.
If you're going to the Great Lakes,
Right.
Sure,
Probably.
but and how windy it is. But like you would have to you'd have to build into your experiment how you're going to control for the size of the waves because
Well,
depending on whether you're measuring from the peak or whether you're measuring from the trough, you can
Right.
get anywhere from 5 to 8 feet.
I agree. If there is waves like that big, for example, we could we could account for them.
Mm-hmm.
We could account for the waves. That's not a big issue. But the main thing
How
is going to
would
be the
you
structure.
Account for
Okay.
them without allowing bias for what you want the experiment to see.
Well, that's the thing. You guys are claiming that the lake is going to have big waves. I would say that on a calm day when the waters are fully at rest. And have you guys ever seen mountains reflecting on a lake, for example?
Yeah.
When it's perfectly still.
Yeah.
If there was waves, that image wouldn't be a perfect, reflection, but it is. So lakes are still. So
They
this
can
experiment, exactly. So we'll wait
But,
for
like,
that day.
it's not like like glassy waters, but even glassy waters, when you look at it, it's not super still.
I guess I get what you mean, but what you're saying is because there's waves, you think there's a curve now?
Well,
I
do
don't
you
get
think
where that's
there's
going.
a lake that still that's 3 miles across?
I
don't
think so.
think
I
that
think we
it's-
could measure easily a lake. There's a lot of lakes that are pretty calm, especially in the mornings when there's not a lot of temperature change, when it's still cold. Usually heat creates, motion because heat creates expansion, right? So it has to be on a very, cold morning,
I just think it's
Not
important
windy day.
to think about when you get whatever data you get.
Right.
How are you going to,
Yeah.
like, how is that objective and not subjective? How
Okay,
are you...
Have you done it? Have you done this experiment?
I don't have the funds for it, but NASA get over $70 million every day from our tax money. They can easily recreate this experiment with $1 million. Easily.
Well, I don't
That's a
think
fraction of their daily budget.
necessary for
I would say it
NASA.
is. If they want to debunk the flat earth, right? Or they should do it.
But they can do it
I
with
think it's
lasers.
already
I would say,
been
again,
done
lasers,
several times.
there's many laser
Unreliable.
experiments. Unreliable. There we go. That's a
They
good
don't travel in a straight line.
Exactly. How do you level out a laser? The irony is you use
They
water.
level themselves, because that's how photons
No,
work.
no, no. When you have a
How do you
laser,
think photons work, though?
well, I'm not familiar with photons, you know?
It's
how
the
photon-
packets of light energy that lasers
No, my
use at
point
a
is that if you're
specific
pointing a laser, right, and what if you're pointing it slightly up? Like, my point is, how do you level it to make sure it's straight? 'Cause
So
you-
we can't build a structure that's 4 inches across to level a laser, but we can build a 3-mile long level structure.
No. My point is that lasers do get leveled. The irony is that they use water to level them.
Use the plumb line.
We could use a plumb line too.
Use a plumb
exactly.
line to level,
yeah,
level a
yeah,
laser.
I agree.
Boom, I just chopped $1 million
Exactly.
off of your budget.
No, here's another thing about plumb lines. If you guys didn't know, all plumb lines, and I guess you guys could look at your engineering class or anybody does. All plumb lines, downward, verticals, are considered parallel to each other, regardless of distance. So again, you could look at engineering. All plumb lines are
I
considered
don't
parallel.
think that's true. Because when the center of the mass
No, on a
is
globe, that wouldn't
on a
be the
globe,
case. But in
like,
reality,
perspective, no, that's reality. But by perspective,
Right.
it might look parallel because here and here might look parallel.
Right.
But like if you take a close up of a basketball close enough, it's gonna look like it's a level
okay.
surface.
Okay, I agree. I get what you're saying, but again, it's not just me saying it; it's what acknowledged, in
Well,
engineering.
let's go back. We can make an experiment to test that.
Yeah, I agree.
So put 2 plumb lines 4 miles apart
Sure.
and see if they're parallel.
That's the thing. How are we gonna measure that they're parallel? I would say measuring the surface of water will be something more concrete.
But that's variable.
Mm,
You would
Yeah.
cut out a lot of confounding variables by using
what variables
a
would I be
laser.
cutting? Oh no. Well, I would say a laser. Again, we have to deal with refraction. We have to deal with the levelness of the laser, which again we could work around. I would say this is still a better experiment.
But so then you don't. That's just fundamentally how physics works in 2023. Is we use lasers to measure a lot of things.
yeah, I
Because
agree.
lasers are extremely precise.
They are. But when we're talking longer distances, because we have an atmosphere, have you heard of refraction? Right?
Yeah.
There's always going to be refraction. We can't suck the air out of the earth,
Sure.
It's
Yeah,
impossible.
but there's always going to be
But-
slight waves.
Yeah, but we can build controls around that to control for the refraction of those photons.
I agree. Again, there's a lot of experiments, probably over 20 experiments online about this, and there's a reason why they're pushing those, because again, it's always going to be inconclusive, and then people are just going to believe what they want.
Sure.
I don't have beliefs. Either I know something or I don't. As far as I know, water doesn't bend. Now, if somebody wants to claim to me that water does start to bend 8 inches per mile squared, then the burden of proof is on the person claiming that it bends. I know you're asking me to prove that it's level, but we all know it's level. People are claiming that it starts to bend after a certain distance. Then you have to prove that.
Well, but
They have.
who's on the burden? Who's the burden of proof on? If you're claiming that it's level, you have to show me that it's level.
Yeah, we could go to any lake and we could see that it's level.
Hey, Tracy,
But yeah, I get it. So
because
you
you're
guys.
the one convincing me.
No.
So
I'm
convince me.
demonstrating how water behaves. Water is not like Jello. It can't support itself. It's always going to collapse and form an equal surface. You go to a pool, go
even
to a
you
lake.
have your straw in there.
Yeah, even if you have a straw, you could put a
But
ball in
look,
here.
the straw. If you look really close, you're going to see a meniscus around the straw because
Yeah.
of the hydrogen bonds.
Yeah, but still it levels out the rest of it though. It might be a
The
little
rest
dip
of
right
it,
there.
sure.
It might be a little dip there, but the rest is still leveled out. So this is at the same height as this. And you could extend this, the water's always going to be at the same height.
But
That's,
if you had a little measuring tape at the very edge here, you would see that it would climb up the edge a little bit.
so you think water is actually slant right here?
I think
It
that it's
goes
climbing
like
up
this.
the edge a little bit. That's how
Yeah.
plants drink. That's how trees
Yeah.
get water to their
Right.
roots.
Even if that was the
Or
case.
to their
When you
leaves.
measure something,
Right, even if
you're
that was
graduating
happening, it's
cylinder,
happening all
you-
around, right?
Yeah.
So you're saying the water's doing this now.
Yeah.
It's
Yeah.
not. So it's not doing this.
No.
So you think it's curving up?
Yeah, when there's
how can
Well,
solid
you're in
surfaces there.
that's a certain container that
Yeah, when you're in like an aquarium.
Okay, but
I don't think we're in an aquarium in terms of a
so
lake.
so in a lake, for example, right?
Sure.
Do you think the water's bending up to the edges of the lake?
How would we measure that?
No, you're claiming that. That's what I'm saying. So you
when
think
it's on like a solid surface, I don't.
In like a
If it was in a glass
like a pool,
surface,
Right.
yeah.
so only in glass. So it
Well, I
goes
mean, it's
up.
it's because glass is usually positively charged.
Right,
but
right. Okay.
Sure.
Well, fair enough. I mean,
Negatively
the
charged.
edges of a
Sorry.
lake are also not the best for that because it usually like the
Because it's
bottom
not even.
is going up
So how do you
steadily
measure-
so that you have like a beach.
Like, how
at
do you
the
get
edge.
good data from?
Right. I guess one of my last questions, I guess.
Sure.
Is there a possibility that we have been lied to about the nature of the Earth and what it actually is, or are you guys 100% convinced that it's a ball?
I think there's plenty of things that we have been lied to about.
Okay.
I don't think that the Earth is one.
Okay, so you're 100% convinced that it's a ball, and you're 100%. And before you guys go, I guess you guys could leave me with something. What's the number one thing that convinces you?
Because that's just how things behave. Why would we
There's a
observe
lot of
other
data.
celestial bodies and then assume that Earth would work differently?
I would say that's like a.
Then we did this whole thing in the 1400s. It's called the geocentric model. People were burned at the stake for saying that the sun
the
was
heliocentric model, right?
The heliocentric is what
Yeah.
people were burned at the stake for saying,
Oh.
because there were religious fanatics that wanted people to.
I've heard those stories. Yeah,
No,
I would say that's
facts.
I would say anything about
That's history.
Yeah, history is in the name. It's his story, so it's
Yeah,
just a story.
Should be their story. Still.
Yeah, but history doesn't prove anything about physics. That's the thing. His history doesn't prove anything about physics. If, you
I
know.
don't think what we've seen here proves anything about this.
Well, how water behaves basically is the level. You guys believe level means curve, then, right?
It depends on the perspective. It
Well, let me
depends
ask
on
you
the
this: what's your
context.
definition of level?
I said it depends on the context.
I'll tell you my definition. You guys want to know my definition of level, or the real world definition that in construction is no deviation in elevation from any given point.
Sure.
So if you have a level surface, there's no deviation from any given point to another. That's a level surface. You guys will have to believe that level means equal distance from the center to the outer circumference of a sphere. That's what level means in the mainstream, in
That's-
mathematics.
The center, when you're talking about, you mean the core?
The core of the Earth, yeah. So the
That's-
distance from the core to the outer circumference is what level means. So that equal distance in your model, that's what level means. So level means curve in your model.
Well, like how do mountains work in terms of levelness for you?
Well, we're measuring it from the levelness of water, the height of a mountain. It's all relative to the levelness of water.
So would you say that my forearm here is level?
No.
Why not?
I don't know. I mean, because it's...
Not like in
Well, like,
orientation,
if you
but like
put
if I put it
this
here,
and you do
is this
it-
level?
No, it's slightly going up.
It's slightly going up. Okay. Okay. So,
This is level. Here it is right here. Right there. That's level right there. Horizontal.
and you just think it's
Oh.
like this all of the time.
Exactly. The Earth is an extended plane. Nobody knows how far it extends. That's what you were saying, the edge. Nobody has found the
Well, I
edge.
feel like level
Why
is
not?
just like
Because
How come?
the international, the Antarctic Treaty, I mentioned it earlier, the Antarctic Treaty prevents any civilians from independently exploring. Again, you can only go on these penguin tours that cost like $20,000, and
Okay.
they hold your hand basically.
how do
You
planes work?
believe in the sun.
Huh?
You believe in the sun.
Well, I don't have to believe it, it's there. I
Right.
accept it, yes.
You accept it.
I accept it.
Do you
I don't accept the stories about it that I
for
told.
okay? So like, do you
Like-
think that it produces heat that
Oh,
helps
yeah.
us here on
Yeah,
Earth?
I can
Okay,
prove that to
cool.
myself, yeah.
Now, how do you know the chemistry of how the sun works?
No, that's where, to me, that's all just stories. Nobody
Okay.
can
What
prove that.
about
But we
sunrise
have
and sunset?
tons of data. No, I have a point here.
Yeah.
Sorry, go ahead.
So we have tons of data on how the sun works, and we
Right.
can independently validate and test that in a laboratory setting.
I mean, when we're talking about like the heat of the sun, yeah, we could,
Yeah,
we could
hydrogen,
change, yeah.
helium,
yeah,
burning
sure.
it produces heat.
Yeah, I agree with that. Yeah.
So, but it also produces other. They're called cosmic rays, but it's basically ionizing radiation.
Okay.
So they're ions that come towards Earth.
Mm-hmm.
A lot of other planets don't have an atmosphere,
Okay.
and that's one of the fundamental properties of keeping life safe next to a star, is
Okay.
because it protects it from the ionizing radiation.
Okay.
It's also ionizing radiation is what gives us like the aurora
Aurora
borealis,
borealis.
yes,
Yeah.
which you can visually see.
Yeah.
Cool. It's part of why the sky is blue is because refraction, which you were talking about earlier, is wavelengths.
Sure,
Blue
I've heard of that.
wavelengths are the
Blue
shortest.
is like the dominant color, right? Or something like that.
They're shorter
Yeah.
wavelengths than
yeah.
like reds.
There we go.
Yeah. And so, which is why during a sunset it gets really red, because the sunlight has to go through more atmosphere, which scatters more of the smaller wavelengths and leaves the longer wavelengths, which are reds and oranges. So, anyways, so we have these ionizing radiations, and one of the reasons that it doesn't destroy life on Earth is that since the rotation of the Earth generates a magnetic field, that's what causes the aurora borealis.
Okay.
So I wonder what you think, how that works in terms of measuring Earth's magnetic field,
Okay, the magnetic field,
which
right.
gives you, it's kind of part of electromagnetism, it's in the name.
Sure.
But I'm wondering how that works if we can show that spinning a liquid metal generates a magnetic field.
Sure.
How would that work
On a level Earth, right?
On a level
Again,
Earth.
I don't have all the answers, so when it comes to what's creating the magnetic field on Earth, you know, I don't know, if I'm being honest. So I acknowledge that there is a magnetic, you know, pull towards the north, right?
Yeah.
That will be considered like a reference point, right? And again,
Which
what's
would be the
causing it
poles.
would be the poles.
South
Again,
and North Pole.
That's the thing. I don't
Which
know
is why that's how the aurora borealis, because that's how magnetic.
there's only, I don't know if you knew though, there's no such thing as a South Pole. There's only a North Pole.
No, there's a South Pole.
I would say
there's
that's a
two
belief.
poles, and you could label them either way, but we've decided that one's
Well,
north,
based
one's
off
south.
of the magnetic radiation,
There
that
has to be
you,
two.
you have to. It moves towards the North Pole from the South Pole.
Yeah.
That's the definition of those poles magnetically.
All right, well, just real quick, I don't know if you guys knew, let me see real quick. Oh, it's right here. So on a level Earth, again, I'm not saying this is what the Earth looks like, because this is just misrepresentation. But if the North is at the center, right? Again, you're asking what's the cause, right? I wouldn't know the cause, but in this model, if you go south, that south is just an outer circumference. It's just a circle. It's any point away from north. That's what south would be. East and west would just be circles around the North Pole, around the center point, right? So when you claim that there's a South Pole, I don't know if you knew, but nobody's actually ever gone to the south. Like, compasses don't point south, they only point north, because that's where the magnetic field is. Now, if you're claiming there's a magnetic field in the south as well, then compasses should point north. As soon as you get south of the equator, your compass should point north. I mean, south. You know, but that doesn't happen. The compass always points north regardless where you are on Earth.
Yeah.
It never points south because there's no South Pole.
No, that's not true.
South is just the opposite of north.
But that's like saying if I leave my house to go to work, there's no my house. There's only my work.
No,
because
south.
That's where I'm
No,
headed.
the pole as a center point.
Yeah.
The south doesn't exist. The south does exist as a
ring
around the
outside.
center point. Exactly. That's how ring magnets work.
So if I'm over here and then it's pointing north, that's your
That's north, and then south will just be opposite of north.
which would be.
But you'll never
into
get to a
the
pole, a
ether.
point. In other words, you'll never get to a point again like you do in the north.
Yeah.
And I don't know if you guys knew this, but the north is actually super restricted, even more than the south. Why? Airplanes cannot even fly anywhere close to the north, and nobody's ever taken a compass and walked around the pole to show, like, oh, this is the center point, and I'm going to walk
I feel like
around.
you can find it YouTube.
Oh, there is one, but it's not very clear. It's like, it's only one that I've seen, and it's just, to me, it's just bullshit, you know. But yeah, there is one that claims that they have gone to the north, but nobody, in my opinion, has actually gone to the true north or the true what's outside, you know, the circumference of. And a lot of people.
So how do they know to hide it if no one's been to the
I think
south?
they might. I
You
think.
just said no one.
No one that I know. Basically, they might have.
Yeah, but no one I know has been to. I don't know. Have
Okay.
you been to Australia?
Put it this
Yeah.
way.
Shit. Okay.
Yeah, the military.
Let's say no one I know has been to Australia. Does that mean Australia doesn't exist?
No.
Well, that's kind of what you're. Concluding.
No. What I'm saying is that, as far as I'm concerned, or the research that I've done, right, or people claiming things, nobody has ever shown any video footage or anything that shows what's beyond, you know. Again, part of the reason is because nobody can just independently explore. You know, you're just, you know, I don't know if this is true, but apparently military will stop you if
I mean,
you
if
have
go
radar and
over
all that.
Borders military
Well,
will
we
stop
Sure.
you. That
have
doesn't mean.
radar.
Yeah, so they'll be able to detect
But-
supposedly and stop you and arrest you with no, you know, without a jury,
I
basically.
guess my last question,
Yeah.
because we have to get back.
Yeah, sure.
but
I actually got
how
to wrap
does-
it up too.
How does seasons work?
Okay, so seasons actually have them here written down. So again, the sun is not what we're told, 93 million miles away and 400 times the in diameter, 400,000 miles. The sun's actually very close and very small. So it's a local small sun. So it's just simply circling above us. So when it's our summer, it's simply just closer to the north, like doing a smaller circle. and that's when it's our summer. So when it's our winter, it's the opposite. So now it is doing a bigger circle, and that's why Australia has opposite seasons to us.
How does it disappear from our view?
Oh yeah, because it's
For
due to
nighttime.
it's due to perspective. So for example, let me see what can I use. So again, because the sun is very close to the Earth, not 93 million miles away. If anything, it's like no more than a couple thousand. I actually don't know the distance.
Oh, we would die, but okay.
No, but it's very small too. It's not a giant gas ball. So it's so when it moves further away, it simply just drops in your field of view due to perspective. So we do have a limit to how far we could see, and that's the horizon. So when it
Why
goes,
do we have a limit to how far we can
because
see?
we're not Superman. So
What if we get a really good camera?
yeah, people have done videos where the sun appears to go down the horizon, and you get a P900 camera, zoom it,
But
and
if
the sun
Earth-
appears to go back up again. And it's due
Where
to
are they
perspective.
taking it from?
Oh, from sea level. A lot of people have done observations like that, where the sun appears to start to go down, and then you zoom in with a camera, and it basically
But
pops
like
back up.
latitude-wise, where?
I mean, that would be kind of insignificant because if it's done at sea level, you know, I guess yeah, I see what you mean, like the distance
Because
that
like
sun's
that's how it
traveling.
works in Alaska.
Right. Okay. But yeah, I wouldn't know the exact latitude measurement again, but I've seen observations like that where the sun appears to go down, but then it comes back up.
I would encourage
by
you to
zooming
look
in.
into where on Earth that was
Right.
done,
Right.
because based off of where it's done, it also affects the perspective.
Right.
So, like, if it's somewhere more northern, like Alaska, Iceland, Greenland,
Right.
that would make a lot of sense. Because
Right.
that's just how the seasons work when you deviate from the equator.
Right. Right. Well, again, the seasons on a level Earth are simply explained by the sun's movement in the sky, and it's a very small local sun. And the reason why we have nighttime is because it just goes out of their field of view, and the light doesn't travel forever, basically. So it's a very small spotlight, basically. It only illuminates. So the sun, whenever it's right above you, that's considered noon, right? So when it's above New York over here, it's noon for them, and we're 3 hours ahead. That's because the sun needs to travel still 3 more hours, and then it's our noon.
So it's never noon right here?
Well, it's never right above you. It's always like an angle like that. You know what I'm saying?
So it's only noon at these specific spots.
I mean, these
it
these
only-
latitude altitude, these lines. If you're in this line when the sun's right here, if you're over here and you could see the sun, technically that's noon. Even though it's not gonna be right above you, it's gonna be like an
But
angle.
if you went here,
Yeah.
the sun would be right above you.
If in winter, yeah, it'll be closer. It'll be more closer to the top.
In any time.
In the summer, it's gonna be slightly lower because it's further to the north. It's closer to the north.
I don't think that's true.
But again, you could, look at this yourself. The
Are
observations
we
of the
in
sun.
the path of noon?
Yeah, we're right here. North America's right here. So our sun, it's
Draw
not.
it like that because
That's the
you
thing.
observed that?
That's the thing. These lines that I just made them for just showing. These are not the exact lines of where the sun's
But
traveling. This is
shouldn't
just
you
for
be able
demonstration.
Shouldn't that be able to be done? You could figure out where those lines are exactly. Because
Well, you would
could
need to know the
look
dimensions of the
and
Earth
see.
completely, and that's one. In my opinion, nobody knows the true layout of the Earth. Not one person knows,
I think
the
that's
true layout.
just your conclusion because you personally don't.
Yeah. Do you guys know the exact layout of the Earth?
Like,
The dimensions. Do you guys know the exact
I
dimensions
feel like
of the
I
Earth?
have data that I believe in. that
Okay,
is-
I'm glad you used the word believe. So you just believe it. You see, I don't believe it. I just don't accept it. If you could prove to me that's the thing. One
Well,
person.
if you sat down with someone, they could prove it to you. I'm just not a physicist.
Right.
Well, you also have to be receptive to it as well.
Oh yeah, I'm receptive. Trust me. But
It doesn't seem that way, though.
Right.
It seems like you are quite close-minded.
no. When
you
it comes
haven't presented me any
no.
data to support
No.
your claims, but you want me to believe you?
No. Don't believe me. These are the claims NASA. This is not my claims, by the way.
Uh-huh.
This is the data NASA's giving us. This is not my data.
Sure.
We're putting that data to the test, and physics, not me, physics, the physics of water, proves that water doesn't bend.
But we
So
found
where's
some
the results
issues.
of these experiments?
Those issues are, I would say, excuses, because the waves on a lake, that's not a good reason to obfuscate this experiment.
Well, if you do this experiment,
That's what I'm saying.
then I would be interested to see the
Oh,
results.
definitely, I would too.
Yeah.
I would love somebody to make this. I actually don't have the funds for this, but I'm hoping that maybe somebody that does have the funds could put it out, once they
I
come
also
across
think
this.
maybe try to think of experiments you could do that don't require that much funding. You can go and look
You can
and
use a
see
bridge.
where the sun is.
Sure, I mean, bridges have been built and they don't take account for curvature. So all of these.
Well, they're not
Hang
that
you-
long.
bridges.
are you
Well,
guys-
could do hang bridges, too.
Are you guys familiar with Euclidean plane geometry?
Yeah.
You know that's the geometry that's used to build everything we see.
Sure, yeah.
We don't use non-Euclidean, which will be spherical. We use planar.
Well, why would
level.
we use non-Euclidean?
Because Earth is a globe, apparently. We should be using
So we just
non-Euclidean.
put circles on circles? And that makes sense?
I mean, if we're building, you know, levels on top of a curved surface, we should take account of that curved surface if we're building levels on top of it.
But we're building it from our perspective, right?
Yeah.
So it depends. If we were building megastructures, we would have to do that.
Exactly.
But from our perspective,
In China, there's a 100-mile-long bridge. That's just one. You know, I'm pretty sure there's many that are miles across.
Sure.
And they have to take account for, and they don't.
so then,
And the Earth is not a globe. And blueprints also show that, basically.
oh, okay.
You know. Yeah. All right, well, I gotta get going, but I enjoyed the chat. Yeah. Yeah, you guys take care.
You too.
All right, man. Ah, fuck. All right, there. I'm calling it already. Fuck. Ah. Oh my god. Oof. God damn. Oof, all right, I'm gonna call it. It went longer than expected, and oh man, that was kind of mind-numbing right there. I mean, if somebody just wants to believe that that water does bend slightly and that waves are gonna make a measurement inconclusive, if they want to just use waves, you know, and stuff like that as an excuse to continue to believe in the globe, then that's fine, you know. But you just can't expect me to go with your line of logic, you know. That's just, it's not gonna happen. I get what you're saying, and I get how you're trying to defend that belief in saying that, oh, but we can't measure water because it has waves. Even lakes have waves. I mean, we all know that on a calm day, you know, the water's, you know, almost perfectly still, you know, when it's at rest, you know, or at least appears. I mean, in other words, no waves. So we should be able to measure it, but yeah, that's just how it is. All right. All right, thanks again for everybody that showed up. I'm gonna go ahead and call it, and I'll see you guys on the next one. Peace.